Hi, it's time for another math easy solution. Today I'm going to go over another video on infinite sequences and series, and now look at some pretty advanced convergence tests, and these are on the Kummer's test, Raabe's test, and look at convergence of the binomial series, which I went over earlier. But now we're gonna look at convergence and more in depth. Anyways, let's just keep going further. There's a note, as always, if you don't have time to watch this whole video, in this video you can play this video at a faster speed. It's a pretty amazing life hack. Your brain gets faster to it gets used to the faster speed, and you could see my recommendations right here for the video speed browser extension and so on. Anyways, you could also download and read the notes. Link will be in the description below, as are the notes on the Hive blockchain in article format. Link in the description as well. And also you could view the video in parts if you don't have time to watch this whole video. And timestamps of all the parts are in the description. Yeah, this is something new I've been doing for the past while. It's pretty amazing stuff. So you can skip to whichever part you want, including even skipping this little introduction, and just scroll to the description, click whichever part of the video you want to watch. Anyways, let's keep going further. So calculus book reference. So note that I mainly follow along the following calculus books: so Calculus Early Transcendental, 6th edition by James Stewart. Yeah, but in this video I'll be also going over some proofs that were from other sources. Anyways, so topics to cover. So recap on the ratio test for convergence, then look at advanced tests for convergence, look at Kummer's test, and then look at ratio test. How the ratio test is just Kummer's test with Bn is equal to 1, and note on Kummer's test. And then look at Raabe's test, which is just Kummer's test with b sub n equals to n. And Raabe's test compares series to the p-series, and then look at corollary of Raabe's test, and then note on Raabe's test and Kummer's test, and then recap on power series, and then I'm going to look at Taylor and Maclaurin series, and then recap on the binomial theorem, and then recap on the binomial series, and then important note on the binomial coefficients, and then look at convergence at the endpoints and how it depends on the value of k. And then convergence of the binomial series, look at endpoint x equals -1 using Raabe's test. Yeah, so basically we'll be using Raabe's test to show that it converges for k is greater than 0 and diverges when k is less than 0. And then look at the endpoint x equals to 1, and then which is an alternating series. And then we're going to be using Raabe's test for absolute convergence when k is greater than 0. And then using alternating series test converges when k is between -1 and 0. And then also look at the pi production notation for factorials, which is pretty interesting. I haven't dealt with that before. And then also using comparison test, divergence diverges when k is less than or equal to -1. And then also note that you could also use the test for divergence, not convergence here. Divergence. Yeah, for this case where k is less than or equal to -1. And also trivial case, k equals 0, converges for all x, and then look at the summary of the intervals of convergence. Alright, so yeah, pretty epic stuff. So now let's just jump right in. So recap on the ratio test for convergence. So recall from my earlier series and in earlier video in which I went over the ratio test to determine convergence of a series. So here's from my earlier videos, linked to the Hive blockchain there, and I've just again screenshot from my calculus book just because it's just more compact. It's typed up, as this one's written by me, and this one's just typed up, so it's compact. So anyways, the ratio test. So if the limit as n approaches infinity of the absolute value of an plus 1 divided by an is equal to L, where equals a finite number L, which is less than 1, then the series, the summation from n equals to 1 to infinity of an is absolutely convergent, and therefore convergent if it's absolutely, if the absolute values of it converge, and it's also converges regularly. Again, as per my earlier theorem, which it's over here. So a series is also from my earlier video. So a series, the series an is called absolutely convergent if the series of absolute values, this absolute value like that, an is convergent, and also the theorem I went over also in that video. If a series an is absolutely convergent, then it is convergent. So again, just recap from earlier video. And now the second part of the ratio test. So if the limit n approaches infinity of the absolute value of an plus 1 or divided by an is equal to L, which is greater than 1, or it goes to infinity, then the series an is divergent. And then for the case where the limit is equal to 1, the ratio test is inconclusive. That is, no conclusion can be drawn about the convergence or divergence of the series AN. So yeah, when the limit in the ratio test is equal to 1, the test is inconclusive. Thus, we need to conduct other tests to determine convergence. And so now we're going to look at advanced tests for convergence. So to go beyond the limitations of the ratio test and other convergence tests that I had covered in my earlier videos, we will consider more, quote, advanced tests. I'll be going over the Kummer test and the Raabe test from the following very well written paper by Sarah Fix from Whitman College in Walla Walla, Washington State, USA. Yeah, it's actually very well written. And yeah, it's oftentimes when I'm reviewing math papers, some of them are just so impossible to comprehend because they skip every step, and they don't explain how they got to point A from point A to point B. But this one is very well written. It's gives you the rationale for each step, and it's very good. Anyway, so this is from this link right there. There's also a local PDF download you could view as well in this archive in case anything happens to the website. So anyway, so advanced test for convergence, Sarah Fix, May 8th, 2019. So the convergence, the first convergence test I will go over is Kummer's test, and which was developed by the German mathematician Ernst Eduard Kummer, born January 29th to January 29th, 1810. And died May 14th, 1893. So anyways, Kummer's test. Let's look at this. Alright, so let the series right here, AN, or the summation from n equals 1 to infinity of AN, be a series of positive terms, and let BN, or you can put it right like that, brackets, let be a sequence of positive constants. Assume that the following limit exists, i.e. is a finite value. So let's say we have L is equal to the limit as n approaches infinity of, this is going to be of Bn, AN over AN plus 1 minus Bn plus 1. Yeah, just put it like that. So these are, so the A's are the positive terms of the series, and the BN's are just positive constants. All right, so now that we have this limit, so the test goes as follows. So if this limit L is greater than 0, then the series AN, the summation AN, it converges. If L is less than 0 and the following series summation n equals 1 to infinity of 1 divided by Bn diverges, then the series, the summation n equals 1 to infinity of An diverges. So yes, if the limit is less than 0 and this particular series diverges, then the series is divergent as well. So you're basically using, it's a type of comparison test with this 1 divided by these constants that we will have to select. So anyways, let's keep going further. So let's look at the proof for this. So we begin considering the case where L is greater than 0. So if the limit is greater than 0, and then what we could do is we could choose a number R such that R is between 0 and L. Then there must exist some integer capital N such that for all n greater than capital N, we must have it such that we have this. So Bn AN over AN, this is A plus 1, this is just a limit. So we're just going to write these terms like that. And then minus Bn plus 1, this must be greater than R. So yes, we're choosing an R between there. So for some value, capital N, it must be greater than it. I'll smooth things around, I'll just illustrate why in a bit. But anyways, we can move this around, or just multiplying both sides by, so just multiply both sides by An plus 1. Let's put a bracket like that. So multiply An plus 1, get rid of the fraction. So what we get is this becomes Bn An minus Bn plus 1 times it by An plus 1. And this is going to be greater than, this is R times An plus 1. I'm just going to box this out. And so now I'll just illustrate what I mean by why it has to be greater than R. So you can just look at the graph like this. So if this is our Yeah, if this is this y-axis, we'll put it as our limit. So if that is our limit, let's write limit. So writing the whole thing out. Limit like that, and then this is our n values. And then basically, if it's approaching a limit L, let's write this as L. Then let's say we have it at 0, and we have just the points. There's the 1, 2, 3, 4, 5, etc. Just keep going like that. These are just each integer point. And then let's say the initial point here is at this point. The limit is that at n equals 1, and then it goes somewhere like this, and it keeps going like that. But since it's approaching this right there, then it has to be. Then you're gonna have a number n. I'm gonna call this n like this, such that, and then draw this in. Oops, draw this in red. So if I draw this in red, and now we're gonna have, I'm just gonna put a line like this. This is R. R is between 0 and 1. So then such that, let's just keep going black. Let's make this like that. Yeah, so such that eventually when you have n is greater than or equal to capital N, so then for all these values, the limit is going to be greater than this R. So that's going to be, let's say at this point here is going to be at this point, and eventually you're going to have, because remember, it's approaching the limit. So it's approaching this limit L, and so on. So it's approaching this over there. This could be anywhere. All that matters for the limit is that as it goes to infinity, you're approaching this right there. So for as it goes to infinity, for some capital letter n, capital N, the limit as n is greater than or equal to this capital N has to be greater than this R. So it's always going to be greater than this R over there. And then if we just do some manipulation right here, algebra manipulation, multiply this by the fraction, the denominator, so it gets rid of it, we get this part right there. So anyways, that's just a visual illustration of that statement. Alright, so now let's keep going further. So now if you look at this equation there, so given any positive integer lowercase m, and starting from n equals to capital N, we have, so we're going to start from n equals to capital N, and then write this out and see what we get. Basically, this is called the telescoping summation or method. But anyways, so if n equals to capital N, we have our limit, or just our terms of the limit becomes this, right? This replaces it with capital N. So we have b. Yeah, let's go back here. Just accidentally pressed enter. So we have bn, b capital N, and then this is a lowercase. A just capital N, and this is going to be minus bn plus 1. Capital plus 1, a capital N plus 1, and then it's going to be greater than R, because this is we're starting off at this point, starting off at n equals to n, starting over there, R equals to, this is going to be R times a capital N plus 1, like that. Yeah, and this will be apparent what we're doing soon. Just because of the way that it's written, we could do a lot of cancellations, because this is just the next terms after it. So now if we do n equals to n plus 1, so just do the next one, what we get is, this is going to be b n plus 1, a n plus 1. And the reason we're doing this is because when we do that, notice this is the same as this one. So that's the same as that. Yeah, this is exactly the same as that, but that's a negative sign. So when we sum these up, they cancel out, become 0. Or yeah, these terms would cancel out. So notice this one right here and that. So that is the reason why we're doing that. And then the next one's going to be bn plus 2, a capital N plus 2, greater than R times it by an plus 2. So the only ones that don't cancel is these ones right there, and also this starting one there, and the last point. That's all I get to. So let's do one more. N equals to n plus 2. This is going to be b n plus 2, a capital N plus 2, minus, this is going to be b n plus 3, a n plus 3. This is going to be greater than, and again, notice this one right here would, this is the same as this one here. So but this is negative. And now this is going to be greater than R times a n plus 3. So if we keep doing this, dot, 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 all the way until a letter m, or positive integer m, so we get n equals to capital N plus, and I'm going to write this as Yeah, the next one I'm gonna put this as m minus 1. M minus 1, and the reason I'm doing that is because, yeah, the reason I'm doing that just for just so that this one right here is, because this is a plus 1. So remember, these are all the plus ones. I want these ones all just to be m, just so it just looks a bit neater. So the next one's going to be b n. This is going to be plus. It's going to be b n plus b minus 1. That's just, remember, that's just n. So if this is capital N, this is n. If this is n plus 1 minus 1, this is n plus 1 minus 1. Alright, just write it like that. And then this is going to be a capital N plus m minus 1. And now the next one here, minus b, this is going to be bn plus m, because m minus 1 plus 1. So that's why we had the minus 1 there, so that it's simpler here. And then next one's going to be b a n capital N plus m. And yeah, because everything else cancels, so we rather have this complicated. It looks complicated, this looks easy. And this is going to be r a n plus m. And now if we sum these up, yeah, if we sum them up, we'll get the cancellations that I was stating. So let's write it over here. So, and then adding these inequalities together, we get cancellations of all of the terms on the left side of the inequality, except the first and the last ones over here. So the only ones we're going to keep are this one right here. And I'm just going to uncircle this. So this one and this one, because there's nothing to cancel those. But if you notice, everything else cancels. Yeah, everything else cancels right here. So this one will cancel with this. So this is b n plus 1, a n plus 1, and this is just negative of that. Likewise here, we'll cancel with this, and then when we keep going down this, we're going to cancel with this and this. So all we're left with is this, and then we're going to be summing up all of these a n's, and we could factor out the r. So we could write this as, so thus we have a bn, a n, so bn, and then a capital N, minus, like this, b, and then we'll have n plus m, and then, yeah, a capital N plus m, like that. Yeah, so now this, on this side, because remember we're adding up all this, and then this is going to be greater than the summation of all these ones. Because each individual one is greater than the right side. So this is going to be greater than r, and let's factor out all these, and we're just going to sum these up. So a n plus 1, and then plus a n plus 2. Let's write it here, a n plus 2, and so on, and then this keeps going on and on, plus dot dot dot, and then plus a n plus n, capital N plus m, like that. Alright, here, just move it over the middle. So now this part right here, this is just the partial sum. This is, we could write this as, like this equals 2, and I'll just write partial sum, because the infinite sum is going to infinity, so this is partially summing, and this is going to be just a summation, and we start off at n plus 1, yeah, summation, and then this is going to be starting off from n equals to capital N, and this is, yeah, this is the plus 1. So this is starting from there to there. Then we're going to go all the way to n plus m. All the way up to capital N plus m, like that. Yeah, just fix up the summations. This is going to be a n. And now what this equals to is, well, we'll just write this as the partial sum. Yeah, this is going to be equal to the partial sum of all the way up to n plus m. But then we're going to be subtracting all the way from the one from n equals 1 all the way to n to capital N plus 1. So in other words, this just equals to the partial sum difference of n plus m subtracted by starting from 0 or 1 all the way up to n plus 1. Yeah, so all it is, this is just a difference. And yeah, actually not subtracting from there, because we're including that term. So just subtract it from the ones before this, which is just n. So yes, that is what it equals there. So thus, we could write this inequality as, using our partial sum notation. So thus, what we get is, let's write it over here. So thus, b capital N, a capital N minus b capital N plus m of a sub capital N plus m is greater than r times it by the partial sum n plus capital N plus m minus partial sum Sn, like that. And we could just box this whole thing out like that. Alright, so now it follows that. So now that we have this, we could move this negative one here multiplied by r, and then move it over, multiply this by r, and move this negative onto the other side. Put this in and shade it, or just like light arrow like that. Just move it over to the that side. Yes, move it over there, and then write this inequality starting from this right side. So we have r times s. This is, did I forget to put a plus m? I think I just deleted that by accident. Okay, so anyway, so that's this one right here, Sn plus m. So now move it over to the other side. Erase this like that. We're gonna get r Sn plus m, so multiply that inside, is going to be less than, because this is just the other side. So this left side is greater than this side. In other words, this is less than this. So just write it over there. And now we're gonna get r, because now it's gonna be the negative becomes positive on this side. So rs capital N. And then we have plus b n a capital N, and then minus right here is going to be b n plus m a capital N plus m. Or we'll just move it to the left, and now we know that these are all just positive terms. Every single one's positive terms. So this one is, this is just positive, or every single one of these are positive, because we had r is defined as greater than 0. Scroll up. So we had r is greater than 0. Yeah, r is greater than 0. And we also have an and bn are positive terms. So we have an is positive terms, bn is a sequence of positive constants. So everything's positive. So in other words, what we have, I'll just put it like this. This, and this, these are all positive terms. Positive terms. That means when we're subtracting a positive term, if we remove that, that means this is going to be less than if we weren't subtracting. So less than r times Sn, S capital N, plus b an an. And in fact, it doesn't matter if these are positive. This one is the only one that matters, because when you're subtracting, even if these are negative, these will just be more negative. Alright, so that's what we have there. So this is going to be less than this right there. In other words, so thus, we have, and what we'll do is divide this all out over to this side. So we divide the r out, so we get just our partial sum Sn plus m, like that. Just fix it up like that. So this is going to be less than, and then write this over here. We divide the r out, so it's going to be now r s capital N plus b capital N of a capital N. Divide this by r. Yeah, so these are all positive terms, and in fact, these are all finite terms. So Sn exists, r exists, these are all, and r is greater than 0, so you're not dividing by 0. So these ones are all going to be finite. Every one is just a partial, it's either a partial sum right here, Sn, it's going to be a finite number. Bn is a positive constant, an is positive term, r is a positive number, and so then this one here is going to equal to a constant. And we'll call that constant c. So in other words, what we have is, thus, the partial sum, Sn plus n, this is a partial sum, this is of the an. So if you're summing up to infinity, it doesn't matter, because it just means that the partial sum as it goes to infinity, it's because we have s capital N plus m, is going to be less than a constant. So in other words, there's a limit to the partial sum. So for all, so it's bounded. And it's not going to infinity. So in other words, it converges. Like that. Yeah, so thus what we have is the sequence of the partial sums Sn, or you could write it as bracket Sn, of the series. Yeah, so the partial sums of this series, this is from n equals 1 to infinity, of an is bounded. And yes, so it's bounded, so it's going to be less than this c, and it's also going to be, likely also bounded below as well. Actually, it is bounded below, so the partial sum is going to be greater than, or equal to 0, because we know that, the terms an, they're positive, so it's going to be greater than or equal to 0, so the first term is going to be, greater than or equal to 0, and the partial sums can never get lower than that, because you're always adding more positive terms to it, and it's also, bounded above, because it's less than the c value, it's constant. So it's bounded and increasing because all of the terms are positive, and so you're always adding a positive to it, so you're always going to get more and more, just bigger and bigger. So it's always increasing but it's capped at below this constant c value. And therefore the series converges by the monotonic sequence theorem, referenced below from my earlier video, and here's from earlier video right here. So definition: if you have sequence an is called increasing if an plus 1 is greater than an, for all n is greater than or equal to 1, and it's all, and yeah, that is, in other words, a1 is less than a2, less than a3. In other words, the bigger you are, the bigger the further down the road of the terms, the bigger. So the terms are getting bigger and bigger. And likewise, it is called decreasing if an is greater than an plus 1. So in other words, an plus 1 is less than an, so it's always decreasing. For n is greater than or equal to 1. And it's called monotonic if it is either increasing or decreasing. And also recall that a sequence an is bounded above if there is a number capital M such that the sequence is going to be less than m. So now note that in this definition, this sequence right here, an, is written as the same as the terms of this series right here, but we're looking at the sequence of the partial sums, which is the summation of all this. So again, that's just terminology. So it's less than this for all that, and it is bounded below if we have it on the other side where an is greater than lowercase m for all n is greater than or equal to 1. And if it is bounded above and below, then the sequence an is a bounded sequence. And then here's the theorem, so monotonic sequence theorem. Every bounded monotonic sequence is convergent. And yeah, it's pretty straightforward. I went over the proof of it, is more abstract, the math of it. So essentially, if a sequence is always increasing or decreasing, hence monotonic, and is bounded above or below, then it will approach a number or limit capital L less than or equal to m, or L is greater than or equal to m if the sequence is decreasing. So in other words, right here, so if it's capped below this capital M, or in other words, this constant c right here, and we're increasing because it's positive terms, so it's going to go approach a limit. So in other words, it's going to converge over to there. So if it's either increasing or decreasing, you can get it something like that. Alright, so let's go further. So what we did was, this is for the case where L is greater than equal, or just greater than 0. So now let's consider the case where L is greater than, less than 0. So in other words, scroll back up. So this was here for L is greater than 0. So let's look at our proof, our Kummer's test again. So if L is greater than 0, we show that it converges. So now the second case, if L is less than 0, and then we also have this series of 1 divided by b sub n diverges, and the series diverges. So let's look at this and prove that case. And again, there is our limit, is bn an over an plus 1 minus bn plus 1. So now let's consider the case where capital L is less than 0. This means that there exists an integer, capital N, greater than 0, such that for all n is greater than or equal to capital N, we get, yeah, in this case, I'm going to write it like this, so bn an over, this is just our limit, an plus 1. Let's write it like this, so an plus 1. It's rated like that. So an plus 1 then minus b, and it's going to be our bn plus 1, and it's going to be less than or equal to 0. And yeah, just write it like that. And this again, this means our limit. So if we have our limit, this is our n, this is our limit, just that limit as n approaches infinity of bn an divided by an plus 1 minus bn plus 1, etc. So, but now we're looking at it's less than, the limit is going to be less than 0. So let's write it above here. So this is n. We have 1, 2, 3, 4, 5, 6, 7, 8, etc. So we're going to look at a case. Let's just look at this case right here where n is greater than or equal to capital N. So just pick our n like that, or just put it below here. So n is like that, just usually put it below the axis. So now we have our limit is going to be like this. Our limit is just going to be like that, L. So it's below 0, so this is the 0. So yeah, so now we're, instead of using our R number, we're just going to use 0. So we're just going to use it like that. So let's say we have our sequence like that. That one's above R, this is below the limit, this is below, this is above, etc. Let's put it somewhere here. But there's going to be a specific number because the limit exists, such that once you get to this number, all of them are going to be below 0. So let's say it goes to there, goes to here, and then they all start converging into this point. So it doesn't matter if it's alternating or not, it's going to go towards this limit. Alright, so now the next step is, well, just rearranging this inequality. So rearranging this one, and then this one would give us right here. So just multiply both sides by an plus 1, and that just cancels over that. So we're just going to multiply it like that, an plus 1. But now, because we have a 0 there, just the right side cancels, so it's simpler than the earlier one. So now we get a b, this is going to be bn, an, this one's going to be minus bn plus 1, and then also move it over to the other side. So then we're going to multiply it and then move it over to this side. We end up having is a, this is going to be bn, bn, an, and then this is going to be less than or equal to bn plus 1 times an plus 1, like that. So yes. Whoops, this would be n. And let's just double check. Yeah, so that looks correct. Exactly here. So multiply this by this and move it over to that side. We get this. And this is again for all n is greater than or equal to capital N. So at a specific point, because again, we're looking at the limit as it goes to infinity, and we know that this occurs. So you're going to have a specific number there. It's always going to be greater than it. The limit's always going to be, or these terms are always going to be below that, or below 0 at this, beyond this number right there, beyond capital N. Yeah, so now what this means is, well, this implies that, yeah, because we have this n plus 1 is going to be greater than this n, we could replace this n with capital N, so that we could replace this by n. So in other words, this implies that b capital N, a capital N, is less than or equal to bn times it by an. Like that. And again, this is for all n is greater than or equal to capital N, i.e. just as in this case above there, just as in this case we have just as, let's write it like that. Let's write J like that. Just as n plus 1 is greater than or equal to n. Well, in our case, it's greater than n. I'll just put equal. Yeah, it's greater than it, because we know it's greater than that. So yes, that is the scenario here. So now we're just replacing that. This is exactly the same thing, but now, so that implies we could just use our capital N number like that, as opposed to our variable, this one here. It could be any positive integer. So now what we have, is, let's just rearrange everything, or we're just going to rearrange this right here, or actually I'm going to divide this out over to this side, and then look at this one separately. So look at this by itself. So what we get is a an, or just look at it this way. So an is greater than or equal to this b capital N, a capital N, and then we're going to divide this by b lowercase n. So in other words, this can be greater than or equal to, let's put it down there, or just leave that arrows, too many arrows, or maybe one or more like that. Alright, so an, the terms, are going to be greater than or equal to b capital N, a capital N, which again, those are just a constant value. So then divided by b sub n, lowercase n. So in other words, this equals to a constant, because remember, those are just positive terms. Bn is going to be a positive constant. An is a positive term, and we know this at a capital N. So that means divide this by, this is just the sequence of it, for whichever value you're looking at. So this is variable, this is constant. So in other words, this equals to c, divide this by bn, like that. Yeah, so this constant number there, c, divided by this bn. Yeah, this is exactly how the series we're comparing it with. Oh, this is a constant times that the terms of the series. So scroll up here, and the proof will be straightforward. So this right here, as we have this 1 divided by bn, so that diverges, and now the terms an is going to be greater than that. So let's just keep going further. So thus an is greater than or equal to c, and then right here, just put it all together. Constant c divided by bn, or b sub n, for all n is greater than or equal to n. Like, I'll just box this all out. So in other words, the terms are greater than these terms. Alright, now that we have boxed this out, so again, so since we are given that this series of the terms 1 divided by bn, so series n equals 1 to infinity of 1 divided by bn diverges, that's based on the test, then the series right here, n from n equals 1 to infinity, the summation of the terms an diverges by the comparison test, because again these terms are always greater than this one, which diverges. Reference below from my earlier videos. Here's comparison test. So suppose that the series an and bn, or these terms an and bn summations are series with positive terms. If the summation of bn, or the series bn, is convergent, and an is less than or equal to bn for all n, then the series an is also convergent. But in our case, we have if the series bn is divergent, so that's our case right here, 1 divided by bn, and these are all positive because this is positive constants, and an is greater than or equal to bn, so that's what we have right here. For all n, then for all n, but in our case, just for all n greater than or equal to capital N, because all that matters is the limit as it goes to infinity. We're not looking at locally. We're looking at convergence, because if it's not going to be going to infinity, you're going to have a finite number regardless. So convergence is based on going to infinity. So if it's greater than or equal to bn for all n, then the series an is also divergent. So yes, so we have proved Kummer's test. And now let's keep going further. So here's a note. So ratio test is Kummer's test with bn equals to 1. So going further, using Kummer's test, if we let the sequence bn, you could write it this way or you could write it like this, but they're just signaling they're the same thing. There's just a sequence equals to so the bn equals to 1. Then we get, just for all n values, it's always going to be equal to 1. Then we get, and I'm just going to write this down. So we have limit. So I'll just write this full on and then put it in. So limit as so L equals limit as n approaches infinity, and I have this ingrained into my brain. So this is going to be bn times it by an over an plus 1 minus bn plus 1. So now these ones are just equal to 1. Equals to 1. This equals to 1 because bn plus 1 or bn is all going to equal to 1. So this equals to, let's put this like this, L is equal to, L is equal to limit as n approaches infinity. Let's write this bit neater. Let's fix that up. So limit as n approaches infinity of, now we just put this in regular bracket. I've been putting it in a square actually. That's because the proof by Sarah Fix was in square ones. But anyways, let's move it over to this. So this is going to be an plus 1 minus 1, like that. So now that becomes this. So now let's look at the ratio, because remember this is, I'm going to show that the ratio test is just Kummer's test with bn equals to 1. So if the limit of the ratio is greater than 1, then L is positive. So if this is greater than 1, then greater than 1 minus 1 is going to be positive. So in other words, if this is just a ratio test, limit as n approaches infinity of like this, an over an plus 1. These are all positive terms, so it could be the same as absolute value. If this is gonna be greater than 1, then L above is gonna be greater than 0. So in other words, this is greater than 0, so the series converges by the Kummer's test. So thus, and just to note, this is the inverse of the the ratio test, because we have this upside down. Ratio test is an plus 1 divided by an. I'll go scroll up to the ratio test to show that again, just to refresh my memory. So the ratio test is an plus 1 divided by an. So that is if it limit equals to L is less than 1, it converges. If it's equals to L greater than 1, then it diverges, and so on. Let's go back here. All right. So in inverting the ratio, we get limit as n approaches infinity, of an plus 1 divided by an. This is going to be, less than 1. For example, i.e. if you're inverting 1 over 2, or actually better yet, just if you have 2, which is greater than 1, then if you invert that, 1 over 2 is going to be equal to 0.5, which is less than 1. Anyway, this should be pretty straightforward if you've gotten this far in the video. Anyways, I just want to put that for reference. So thus this series also converges by the ratio test. So if this limit is greater than 1, then Kummer's test said it converges. But then if you invert that, you have this test is converges also by the ratio test. So all we need to do is check if it's greater than 1. And so And here's again for reference, copy and paste it over here, closer to it instead of scrolling. So ratio test, yeah, so it's equals to L less than 1, it's convergent. It's absolutely convergent, is therefore convergent. Similarly, if the limit of the ratio in Kummer's test is less than 1, then L is negative. Yeah, so I'll write if, let's look at the ratio, I'll put this in bold as well. So if the limit which is inverse of the ratio test 1, so limit as n approaches infinity of an over an plus 1, an plus 1, if this is less than 1, then L is less than 0, because you're going to have, scrolling up here, yeah, less than 0. You have this 1 there. So if this is less than 0, a number less than 0, less than 1. If this is less than 1, subtracted by 1, it's going to be, well, it's going to be negative, because that negative 1 is absolute value of it is greater. So, yeah, so thus the series diverges by the Kummer's test. And I just want to note, though, because we know that the ratio, or the Bn that we have compared with, scroll back up here, so we have to compare with this one over Bn, but our Bn is going to be 1, and the summation of 1 is just going to be, well, 1 plus 1 plus 1 goes to infinity, so diverges, so I'll write note. Yes, if I put a note like that, summation up to infinity of n equals to 1 of 1 over Bn, so the series like this, and we know Bn is just going to be equal to 1, based on, we're setting it equal to 1, to show that it's the ratio test, set it equals to 1, like that, Bn. This equals to summation. Yeah, this equals to summation from n equals to 1 up to infinity of, now we'll have 1 over 1, which is just 1. Yeah, so 1 over 1, let's put it for completeness. This goes to, like that, n equals to 1, 1 equals to, well, 1 plus 1 plus 1, so you're going to infinity. You're going as large as n is, plus 1 plus dot dot dot. And this is going to be diverges. Diverges to infinity. Yeah, so, and the inversion of this limit yields, and just write limit as n approaches infinity, and we're going to reverse that, so an plus 1 over an. So if this was less than 1, that means the inverse is going to be greater than 1. And this is going to be divergent from the ratio test. I.e., again, if you have, so if you have 0.5, which is less than 1, now if you invert that, 1 over 0.5 is the same thing as saying, well, 1 over 2, the 2 goes on top, this equals to 2. Yeah, or 0.5 goes into 1 two times, and this is greater than 1. Again, that's just basic algebra. I'll just put it like that, and then put this not as bold. 2 greater than 1. Yeah, so likewise, this series diverges by the ratio test again. So if it's greater than L, if L is greater than 1, it's divergent as by the ratio test. And therefore, we can conclude that the ratio test is simply Kummer's test associated with the sequence Bn equals to 1. So yes, so that's fascinating stuff. So note on Kummer's test. So Kummer's test is inconclusive when L is equal to 0, but when this happens, it is possible to refine the sequence Bn to give a result, which is why the case when L equals 0 is not included in the definition of the test, because you could always change your Bn. But because there's no specific strategy for choosing B sub n, this can become a tedious and time-consuming task in order to find a sequence that yields a result when used in Kummer's test. And this is where Raabe's test comes in. If I'm pronouncing it differently, wrongly, let me know. Anyway, so Raabe's test is simply a specific case of Kummer's test where we let Bn equals to n. Therefore, we do not have to go through the process of trying to find a suitable n. We could just use Raabe's test. And Raabe's test was formulated by the Swiss mathematician Joseph Ludwig Raabe, or Raabe, however you want to pronounce it again, let me know. And he was born on May 15th, 1801 to January 22nd, 1859. So he was around at the same time when the Kummer was around. And this is stated below the Raabe's test. So Raabe's test, Kummer's test with Bn equals to n. So let the summation from n equals 1 to infinity of an be a series with positive terms, and assume that the following limit exists. And again, they're all dealing with positive terms, or more specifically, just as long as the terms are the same sign, because you could always just multiply by a constant -1 if it's negative to get them all positive. And so assume that the following limit exists. I is finite, so we have. This time we're going to use, instead of using L, we're going to use the Greek letter rho. I'm going to write it like this, just to make it not look like a P. So it's sometimes written like that. I'm going to write it like that. So rho is equal to limit as n approaches infinity of... now this becomes, because bn is equal to n, we could just factor out the n. This could be equal to n an over an plus 1. This is a bit big right there. And then minus 1. So yes, we have that n. So if you multiply this n inside, you're just going to get n times an over an plus 1, and then minus n. But we just factor out the n like that. And I'll go over the proof of this. Is the same thing as the Kummer's test. But anyways, this is Raabe's test, and if the rho is greater than 1, then the series summation n equals 1 to infinity of a sub n converges, and if rho is less than 1, then the series summation from n equals 1 to infinity of an diverges. So so this one doesn't have the comparison test for this Raabe's test that we had before, where 1 over bn diverges. You have to make sure that diverges to do that. And in fact, this Raabe's test was made before Kummer's test. So yes, this is how it's written. So anyways, and then the third condition, if rho is equal to 1, then the summation n equals 1 to infinity of an may either converge or diverge, and the test is inconclusive. So when that is equal to that, is inconclusive. And just note, rho is the Greek letter rho. It looks like a P, but I'll put this curly sign there. Is usually how it's written. That's how I wrote it in university, just to make it not look like the P. Because this one, you could write it like that. It looks like a P. So anyways, proof. So parts I and double I, or I and number 1 and 2, are consequences of Kummer's test. To demonstrate this, let bn equals to n and compute. So we're going to write this as, using Kummer's test, we'll write this as L equals to the limit as n approaches infinity. And now we're going to write the full Kummer's test. Bn, remember bn is going to be times it by an. an over an plus 1 minus bn plus 1, like that. And now for our case, well, we have this is going to be n. That equals to n. This n plus bn plus 1. Remember, bn is just n. This is n plus 1, like that. So what we end up having is this equals to limit as n approaches infinity of... Now we're going to have an n times it by an over an plus 1 minus n plus 1, like that. Now we could use our square brackets to differentiate the brackets, like that. And then what we get here is, to simplify this even further, limit as n approaches infinity, and now replace this is going to be n times it by an over an plus 1 minus, that's going to be minus n minus 1, like that. And here I'll just keep going further. We can actually let's just factor out the n right away. So we'll factor this out. So minus 1, and move this all out and write it like this. Put a big square like that, just to save time or save space. So that bracket, just get rid of that bracket. It's going to be minus n, factor out the n, so we have it like this. And this is going to be limit as n approaches infinity of, and it's going to be a square bracket, this one, of n times an plus, of an divided by an plus 1 minus 1, and then close bracket, and subtracted by 1. And now you could separate this limit into, just using the limit laws, limit as n approaches infinity, and this is going to be equal to n, which is going to be, now this is our Raabe's test, minus 1, like that, and then minus the 1 over there, limit as n approaches infinity of 1. Well, this is limit as 1, there's no n there, it doesn't change, so this just equals to 1. Equals to 1. So in other words, we get In other words, we get this one right here. This is just our row. This is just our row. That is just a Raabe's test like that. That's the limit is equal to this one. So in other words, we have our L from our Kummer's test is equal to rho from Raabe's test minus 1. So we could box this out. Yeah, so now that we have this, if rho is greater than 1, then L is greater than 0. That's just the Kummer's test. So yeah, so if rho is greater than 1 for the Raabe's test, then rho is greater than 0, so then the series summation from n equals 1 to infinity converges by Kummer's test. Similarly, if rho is less than 1, so if it's less than 1, then we're going to have less than 1 minus 1, it's going to be negative, so then L is less than 0. And recall that the summation n equals 1 to infinity of 1 divided by bn, again we're using Kummer's test, this equals to the series 1 divided by n. So from summation from n equals 1 to infinity of 1 divided by n, so that's bn equals to n. And this diverges as referenced below, that's just a harmonic test. Thus the series summation from n equals 1 to infinity of an diverges by Kummer's test. So in other words, we just use Kummer's test, which we proved, to prove Raabe's test. In other words, Raabe's test is a specific case of Kummer's test, even though, interestingly, Raabe's test was first found before Kummer's test. So going further, or here's just a recall from earlier video, this is the p-series, so this right here, 1 over n. Recall this, the p-series, summation from n equals 1 to infinity of 1 divided by n to the power of p, is convergent if p is greater than 1, and it's divergent if p is less than or equal to 1. And note that when p equals to 1, that's our case, so 1 divided by n to the power of p equals to 1. It is often called the harmonic series and has to do with musical notes and so on. So if the result of Raabe's test is p or rho equals to 1, then the test is inconclusive. Because we get the case L equals to 1 minus 1 is 0. Yeah, and yes, it's inconclusive for the Kummer's test, but we don't include that in Kummer's test because you could change the bn and see what you will get a result. Alright, let's go further. So Raabe's test compares series to the p-series. So applying Raabe's test to the p-series, the one listed above here, gives us, and what we get is, let's just write our p-series is equal to, so p-series we have summation up to infinity of n equals to 1 divided by n to the power of p. Yeah, and first of all, yeah, so we already used the proof and showed that we had to compare it with the p-series right there, where n equals to 1. But now if we just apply to the p-series, so this one right here equals to, where we're going to apply to it, so we're going to pick our an, is going to be the p-series term, so 1 over n to the power of p. Yeah, so let's apply Raabe's test, so let's write the rho, so again, it looks like p, so let's write it with the curly sign. Rho equals to, let's write this better, rho equals to limit as n approaches infinity of, we have an over an plus 1, and this is going to be minus 1 like that, and we're going to throw this an inside there, which is our 1 over n to the power of p. So this is equals to, let's write it over here, limit, write this better, limit as n approaches infinity of, now we get, this is n, 1 over, let's write it like this, so an is going to be 1 over n to the power of p, and then this one right here, an is going to be, well, 1 over that, so let's put that, invert this one, this is going to be 1, so the inverse of that, 1 over n p plus 1, actually not p plus 1, this is n plus 1. To the power of p, because yes, we're putting in the inside the n, so it's going to be n plus 1, and it's divided by, and then this is already a fraction, so it goes on top, and then this is going to be minus 1, like that. Alright, let's simplify this even further, so this equals to limit as n approaches infinity of, now we're going to multiply this inside, this n inside, so we get a n times it by, and also this one, the same powers, we can just use our power laws and merge those together. It's going to be n plus 1 over n, like that, to the power of p minus n, like that. And now what we'll do is, we're doing a limit, so let's multiply, usually the method is multiply the top and bottom by 1 over the highest power here. I'm not going to do that Yes, yeah, just 1 over the highest power of this n that's external, so we can do some cancellations and get it in a form we can utilize. Again, using which we will use L'Hopital's rule. So anyways, first of all, this would cancel with this, and then we're going to get 1 over, it's going to be 1 plus 1 over n. And then this cancels with this, with these two, and then we're just left with that one there. So this equals limit, and let's just do this a bit differently. Yes, remove those cancellations. I'm going to slash it this way to indicate that why we're slashing. So this one is these two because of this. This one is because of this right here. And it's going to be a big block like that. Limit as n approaches infinity. And now we're going to get a term. So this is going to be, it's going to be a division. 1 over n like that. And then we have a 1 plus, this is going to be 1 over n now. And then this is going to be p, power of p, minus, this is going to be, cancels, goes to 1. Goes to 1, like that. Yeah, so that's what we have there. And now when you plug in infinity there, we get a, this part's going to go, put it lightly, 1 over infinity goes to 0. This one right here is going to go to 1 over infinity goes to 0. So in other words, we're going to get a 1. It's going to approach a 1 over 0, which is approaching a 0 over 0, which is undefined. Yeah, it's undefined or indeterminate. So let's put indeterminate. So we could use L'Hopital's rule, indeterminate or undefined. Alright, so now to solve this, we could recall L'Hopital's rule. So, yeah, because this is an indeterminate form. So recall L'Hopital's rule for evaluating, quote, indeterminate limits from earlier video here. And, yeah, so suppose f and g are differentiable and g prime of x is not equal to 0 on an open interval I that contains a, except possibly at a. And suppose that the limit as x approaches a of fx is 0, and limit as x approaches a of g of x is 0, or the limits go to plus or minus infinity, and yeah, both of them go to plus or minus infinity. In other words, we have an indeterminate form of the type 0 over 0, or infinity over infinity, in our case 0 over 0. And then the limit as x approaches a of fx over g of x is equal to the limit as x approaches a of f prime of x over g prime of x, again, where g prime of x is not equal to 0 on that interval we're looking at, except possibly at a. So if the limit on the right side exists or is infinity or negative infinity, yeah, so it yeah, so we can just take the limit of the derivatives, and then yeah, we'll get the result. If it's infinity or negative infinity, yeah, then that just says the limits are going to infinity or negative infinity. So anyways, so that is limit, yeah, will just be diverging. So let's just solve this right now. So thus the limit becomes, and we'll write it as, remember this is rho, and this is this term right there, but we're going to be looking at the derivative. So let's write this as rho equals 2, and I'll write the h for L'Hopital's. Yeah, notation, it's usually how it's written, or sometimes it's, I've seen that it's a pretty good shorthand notation. So limit as n approaches infinity of the derivative d over dn of 1, yeah, 1 plus 1 over n, and then this is p, and then let's do that minus 1, put a bracket like this, and then divide this by, yeah, divide this by 1 over n, derivative of that, so d over dn, 1 over n, like that. And now this equals to, well, the limit as n approaches infinity of, now this derivative of this this term right here, that's just a power rule. We could use our power rule. P goes down, so we have p times it by 1 plus 1 over n, and then we have we subtract the power, so p minus 1. And then using chain rule to get the derivative of the inside, because in terms of n right there, there's 1 over n, and derivative of that one is, that's going to be, this is going to be negative 1 over n squared, is the derivative of 1 over n there, and I'll do that over here as well, the same thing over here, negative 1 over n squared, and the derivative of this 1 is 0, so we just leave it like that. So divided by 0, it just goes away. And again, note here, I'll just put a d over dn of a 1 over n. This just equals to d over dn n to the power of negative 1, and then using power rule, this just becomes, the negative 1 goes down, and then we subtract the power. So it becomes like that, which is the same thing as negative 1 over n squared, like that. I just put a bracket. And that's the same at the top and bottom. So in other words, what happens is this cancels with this. So those are just cancels. So we get rho is equal to limit as n approaches infinity. So yeah, just a rho and there's p, they look similar. So there's going to be p over p times 1 plus 1 over n power p minus 1. And now, as n is going to infinity, this is becoming, well, 1 over infinity, which equals 0. So it's approaching 0. Yeah, let's put a 0 there. So in other words, this is going to 0, and then what happens is, yeah, then we're just going to be left with 1 plus p to the power of, 1 plus to, or just 1 plus 0 to the power of p minus 1. In other words, this whole thing just becomes 1. Yeah, because 1 to the power of anything, it's going to be 1 times 1, 1, etc. So it's just equal to 1. So then this is going to be equal to p. Like that. Now let's write p like that. In other words, we have rho is equal to p. Yeah, so what this means is now, so thus if rho is greater than 1, then the series converges by Raabe's test. Again, just to recap on Raabe's test over here. So if it's greater than 1, it converges. If it's less than 1, then it diverges. And then if you compare that with the p series, if p is greater than 1, it is convergent if it's and it's divergent if it's less than or equal to 1. Yeah, so less than or equal to 1, but in this one case, if rho equals to 1, then this may converge or diverge. But for the p-test, it's divergent. Let's going further. So this implies that p is greater than 1. Yeah, so when rho is greater than 1, p is also greater than 1, which indicates that that series is a convergent p series. So it's convergent by the Raabe's test and p series. And on the other hand, if rho is less than 1, then we know the series diverges by Raabe's test, and this implies that p is less than 1. So yeah, when this is less than 1, this also implies that p is also less than 1. So when rho is less than 1, p is less than 1, and therefore the series is a divergent p series. This demonstrates that Raabe's test, Raabe's test tests a series for convergence by comparing the series to the p series where rho or p equals to rho. And then when it's equal to 1, when rho is equal to 1, well, we compare that with a p series. That's just a p series where it's equal to 1. That's the harmonic series, and that diverges. So yes, it's a very fascinating scenario here. So that's what the Raabe's test does. It essentially compares with the p series built into the limit. So now continuing further, there's a corollary of Raabe's test. And here I quickly just added a notes. MES note, corollary means a proposition or statement that directly follows from one that is already proved. So yeah, so we just proved Raabe's test, and now here's another proposition or statement or corollary that follows from the test. So in general, when rho is greater than 0, the sequence an converges to 0. Yeah, as n goes to infinity. So proof of this one right here. So this is a very interesting one. So if this is greater than 0, in general, this is going to be approaching 0. So proof, when rho is greater than 0, there must exist some integer, capital M, such that for all n is greater than or equal to m. And this is going to be the same thing as earlier. So if we look at our rho, so the rho is the limit as, let's go here. So our rho is equal to limit as n approaches infinity of n over n times an over an plus 1 minus 1. So now if rho is greater than 0, then that means we'll have a term like this, greater than 0 for all n is greater than or equal to m, just as our earlier derivations. So if we have, actually we don't need to write rho, so we'll just write n. So we need to have an n times it by an, which is the terms inside the limit, an plus 1 minus 1 is going to be greater than 0 for all n is greater than or equal to m. And again, this is because if we draw the graph, just to visually see this, so if we have n like that, this is the limit, like that. Actually, the phrasing here, limit, is actually a bit misleading. It's actually just this number. So the y-axis is that. I'll just put a y. Yeah, let's put it like that. And yeah, might as well change it for the other ones because I put limits for that, but it's not actually a limit. But because it's just a term. The limit is over here, or the limit is over here. So this one, I'll just put it like that, y. Like that. That's just this term, those terms over there. And then I had one more, so over here. So this right here, I'll just put the y, that's this part right here, put it in, put this like that. Yeah, so that's the limit here, just to be more accurate. So anyways, let's keep scrolling back down, and now let's look at our number here. Okay, so we have here, so this is going to be greater than 0, and that's because, well, we know our row is greater than 0. So this is 0. This is going to be our row, our limit. Write it more like a row, so it doesn't look like a P. Alright, it's going to be like that. Yeah, then there exists a number, this is going to be capital M, such that, again, when you're going beyond this for n is greater than or equal to capital M, then this limit, or this row right there, these terms are going to be less than the row. So, not less than row, it's going to be greater than 0. So, remember, if you have n like that, 1, 2, yeah, etc. So the terms could be over here, it could be here, it could be negative, etc. And yeah, just to say it goes here. But then there's going to be a specific point here. Yeah, greater than, yeah, so there's going to be a specific number or integer m, such that whenever n is greater than it, then it's always going to be greater than 0. Put this over here. And that's because the limit is approaching row, where row is greater than 0. So yeah, so it's approaching that. So we're going to have that scenario as per usual. And let's just fix this to make it a bit more, look a bit more nice. Let's put this over here, and let's put this one over over here. And then yeah, this one's below, and all of a sudden, yeah, above it there. All right. Yeah, so now it follows that, what we'll get is, let's just write this down again, but over here, so we have n over an plus 1, and then minus 1, this is greater than 0. So now we just divide by n on both sides, divide by n, this just stays 0, this cancels. So what we're left with is an over an plus 1 minus 1, and they're greater than 0, or we can just move this over, move this negative 1 to this side, so we get, just simplify it further, it's greater than 0. So in other words, move this over here, and then we're going to get an is greater than an plus 1, and this is for all, or I'll move it actually somewhere here, or I'll just move everything to the left, move it over here. So now we have this, an is greater than an plus 1, so in other words, the terms are getting, are decreasing, so an plus 1 is going to be less than an. So for all n is greater than or equal to capital M, and I'm just going to circle this like that. Alright, now this tells us that the sequence an is eventually decreasing once n gets greater than or equal to capital M. Therefore, the sequence an converges to some number L. So if we have graph this out, and now the y-axis, we know this one is our an terms. Yeah, so it's going to be decreasing, and let's put a n like this. Actually, yeah, so let's say we have our points, this is our n. So it's going to be a point here, capital M, that for greater than it, so n is greater than or equal to m, is going to be decreasing. And then, so the limit's going to be somewhere like this. Let's go over here, so this is 0. And remember, these are all positive terms. All the ANs are positive terms, as per Raabe's test. So this is going to be just random points like that. And it keeps going on and on. We'll spread this out like that. And then this goes, here's L. Yeah, so it's going to have some number there. So once it gets to this point here, it's going to be decreasing. So once it gets past the M, it's going to be always decreasing. Yes, it's always going to be decreasing, getting closer and closer to this L there. Because it's just decreasing. So it keeps going on and on there. And also note over here, before this N, it could be anywhere. It could be increasing. It could be below this, etc. And just put another here, another here. So yeah, but eventually it has to be decreasing once it gets past this N right there. Or actually, better yet, more accurate, it's going to be, this would be above here. so that from here to here is decreasing. So yeah, greater than m is decreasing. Yeah, so that all the an plus 1s are going to be less than the previous. So this is less than previous, and it keeps going on and on. Alright, so now going further to show that L equals to 0, and again that's because over here, so it's decreasing, so this limit goes to the sequence of an goes to this limit L, but our corollary says that when rho is greater than 0, the sequence an goes to 0, it converges to 0, in other words L equals to 0. So to prove that, or to show that L equals 0, we use proof by contradiction and assume, so we'll assume that L is not 0 and L is greater than 0. So assume that, and we're going to prove that it's a contradiction, so that, and by contradiction we'll show that L is equal to 0. So similar to our above reasoning, as we were doing all the time, drawing the graphs, because rho is greater than 0, there exists some integer capital N and a number epsilon greater than 0, such that for all n is greater than or equal to n, and also note epsilon is a Greek letter, just Greek letter epsilon, written like this, like an E. Yeah, so there exists some integer capital N, and this is going to be, so and a number epsilon greater than 0. This is when rho is greater than 0. Again, remember the Raabe's test. Rho is greater than or equal to limit as this, n approaches, as n approaches infinity, you have n times an over an plus 1 minus 1. So we'll look at this term. This term needs to be greater than epsilon. And again, exact same thing as we had over here. This one where we had it greater than 0, but now we're just going to be looking at another number here, epsilon. So somewhere in between, because rho is greater than 0. So let's just write that down over here. So we're going to have an n times it by an over an plus 1 minus 1 greater than, this is going to be epsilon. And again, if I draw the graph just for completeness, because I am a visual person, so this is going to be our, let's put that there, this is going to be our y, this will be our n, we have terms, we have the n terms like that, and we're going to have a letter, capital N, somewhere over here. Yeah, such that, and we know rho is greater than 0, so that's our rho. So we're going to have, and we're going to draw this one in red. Just put a line like that. And let's draw this over here, red. So we're going to have an epsilon here, like that. Whoops. Alright, now we draw it back, this one. Alright, and okay, so now that we have this, we're going to have it such that greater than n is greater than or equal to capital N, then all of them have to be greater than this epsilon. So it has to be greater than this line there, because remember the limit is approaching over here. So the limit's approaching the rho, so it's going to be greater than it, but before it could be less, it could be whatever, etc. Let's put another one here, and so on. So as long as it's past this capital N, and yes, so we have that. Alright, so now from this, we see that, and basically we're going to take this and rearrange it as per usual, and then what we get is, let's just write that down, so we get an over an plus 1 minus 1 is going to be greater than epsilon. And now the next step is, well, we're just going to divide this out by n, so or just move it over to here. So I should divide both sides by n, or just move this side over there. So we're going to get an over an plus 1 minus 1. It's greater than epsilon over n. And now the next step is, well, we'll just multiply both sides by an plus 1, so get rid of this denominator right here. And then what we have after that is we get an minus, and then 1 times that is just an plus 1. So we're multiplying this on every single term. And then greater than, and this is going to be epsilon over n times it by an plus 1. And we can go further. So this inequality there, this is also going to be greater than, well, because we know, look at this an plus 1, this is greater than L. And that's because, remember, this is, we already showed that this is an, the sequence is eventually decreasing. So past n is greater than or equal to m. And then therefore an converges to some number else. In other words, it's decreasing because the next term is always going to be less than the previous. So then it's decreasing, so then L is going to be less than any of those values for n is greater than or equal to m. Yeah, so now that we have that, we could write this as, because remember this is it's greater than L for n is greater than or equal to m. And then although this one is for greater than or equal to n, this is for the row or the Raabe's test limit. This one is for an, but essentially what it means is just as it goes to infinity, you're gonna eventually have both cases to be true, which is gonna be this is gonna be greater than epsilon, and you're gonna eventually have this is gonna be greater than or equal to n, where it's decreasing. So you're eventually gonna get to a point where it's decreasing and greater than epsilon. Yeah, so let's just write this down. So this is going to be greater than epsilon over n times L, which is our limit as an approaches infinity. Alright, so now that we have that, and now what we can do is, quote, telescoping. Again, this difference gives us whenever lowercase m is greater than n, which is greater than or equal to capital N. Again, this telescoping is just a way of expanding terms that are like this and then shrinking them down by eliminating everything. Basically, remember we have an and then we have an minus an plus 1. So then when the next one, we're going to have an plus 1 on this side and then negative sign on the previous. So the signs change, we're going to cancel. So let's start again, similar to before. So n, let's start at n right here. Yeah, let's put n like that. So then the first term is going to be, well, an minus an plus 1 is greater than epsilon over n times L. And then the next one is going to be n plus 1, and then we're going to get an plus 1. Yeah, so an plus 1, then minus, then one next to it, the next one is going to be an plus 2, because n plus 1, then you plug that n inside. So n plus 1 plus 1, n plus 2, greater than, and now we're going to have, the next one's going to be, and let's just write this as EL, and then just put this here, 1 over n plus 1, or just write it like here again. So epsilon L over n plus 1. Because remember, that's n, this is n. This is n plus 1, this is n plus 1. And now the next one, as per usual, n plus 2. Because remember, when we sum these up, notice what we'll have is this will cancel with this when we sum these up. All we're going to be left with is the first one and the last one, and then this one's, and then on the other side we're going to have a bunch of terms adding up that are similar. This is going to be an plus 2 minus an plus 3. This is going to be greater than epsilon L over n plus 2, and so on. And we're going to go all the way to the mth integer, or the integer m, so it's going to go all the way dot, dot, dot. So we're going to go to m, but we're just going to, we want it simpler, so we're going to subtract m minus 1. And then, so then we're going to write now the reason for this, because those are the parts that are going to cancel. So m minus 1 is over here, and the next one is going to be minus am. Yeah, so they're just simpler like that. So then this would cancel with this, and then this would cancel, etc. Dot, 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 all the way, and this will cancel. And this is greater than epsilon over, epsilon L over n plus m. Yeah, n plus m minus 1. Actually, no, this is not n. This is just m minus 1. Yeah, that's just m minus 1, because remember, n is n plus 1, n plus 1, n plus 2, n plus 2, m minus 1, m minus 1. So in other words, now we're going to, put a dot, dot, dot everywhere. So now we're going to add these all up, and those are the cancellations, and we're just going to be left with that and this. And so we're going to write this down, summation, we're going to get this equal to an minus am. And it's greater than epsilon L, and then the other ones are all the, all similar terms, put them all together, is going to be now 1 over n plus, just factor out the constants epsilon and L, 1 over n, and then plus 1 over n plus 1, plus 1 over n plus 2, etc. And it goes all the way, just leave it like that, plus dot, 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 all the way to plus 1 over n, n is going to be the n minus 1. n minus 1, like that. Yeah, so that's what we have. And we know this one already. This is just 1 over n, and 1 plus, then plus, 1 over n plus 1. In other words, that's our harmonic series, which is p series equals to 1. Let's scroll back up to our p series. Remember, the p series, 1 over np, is convergence if p is greater than 1, and it's divergent if p is less than or equal to 1. And that's, again, called the harmonic series. So that's just a harmonic series. So harmonic, I'll just call this, this is right here. Yeah, let's just put it down here. So this is just a harmonic slash p series. P equals to 1 series. Put the p equals 1 bracket like that. So p equals 1 series, p series. And this diverges. So we know this diverges. So then this difference is greater than a divergent series. So in other words, that's stating that an diverges, because you're going to have an an minus an am, and these should be finite. So that's supposed to diverge. Yeah, so going further, so since a sequence of partial sums for the harmonic series, p equals 1 series, diverges, and we know that an converges, i.e. to L. Remember, we know that an is decreasing and converges to L. So we already know that, so it can't diverge. So that's a contradiction. And so we have reached a contradiction. Therefore, the sequence is, or the sequence an converges. Converges to 0. That is, L equals to 0. And we could see that from here. And the reason is, because remember, if this is divergent, the only way that's possible is if this L is equal to 0. Yeah, so we'll just write this down right here. And actually, I'll just just check up on this and I'll just move this over here. So it's just saying that we're summing up all these terms. Not necessarily, it's just not a series of an minus am. Yeah, rather all these sum up to these two terms right there. So going back here, so if we write this out, we get, well, if we think about this one, we get an minus am. Yeah, this is going to be greater than epsilon times L times a divergent series. Remember, times divergent series either plus or minus infinity. In this case, that's infinity. So, yeah, divergent series, let's put it like that. Yeah, divergent series. Yeah, or in other words, you could write it just like this. Epsilon times L times infinity. Like that, but the only way that this is possible is because, remember, we know this converges to 0. So that's the only way is if this is equal to 0. So if the L is equal to 0, then, because we know that this is convergent. This is divergent on the right side, these convergent on the left side, so then that's only way is if L is equal to 0 for the trivial case. And then we get is, well, an is less than am is greater than 0. And then move this over to this side, and then we get our starting point where an is greater than am. In other words, it's decreasing because am is less than an. So since we know that, since m is greater than n, we were given that as expected. So it's decreasing. And so it's decreasing as expected from our earlier scrolling down here where we found the limit converges to some number L, and that's because it's decreasing right here. An is greater than an plus 1. Yeah, so now that we have this, and thus we have proved the corollary, the initial one scrolling up here, where if in Raabe's test in general, when rho is greater than 0, the sequence an converges to 0. Because remember, it's again, it's decreasing, and all of them are positive integers, so you're going to have an L over there that's greater than or equal to 0. And then if we assume it's greater than 0, we end up having a contradiction, so thus it is equal to 0, the limit. And so lastly on this Raabe's test, a note on Raabe's test and Kummer's test. Raabe and Kummer had worked on power series at about the same time during the mid-1800s, but it was Raabe's test that chronologically preceded Kummer's test. So instead of considering Raabe's test to be a refinement of Kummer's test, we could also consider Kummer's test to be a generalized version of Raabe's test. So yeah, because remember, Raabe's test is essentially the general case of Kummer. It's a specific case of Kummer's test where Bn is equal to n, but Raabe's test preceded that according to mainstream history. Yeah, it preceded Kummer's test, so nonetheless, you could view that Kummer's test as the generalizations of Raabe's test, or vice versa, the other way. You can view Raabe's test as a refinement or a specific case of Kummer's test. Or yeah, since chronologically you could consider Kummer's test generalization. Anyways, so that is the proof for that, and we're going to be using Raabe's test specifically for the binomial series convergence. Alright, but first let's go over a quick recap on power series and then binomial theorem and so on. So here's a quick recap on power series, which are a specific type of series. So it's written like this: summation from n equals 0 to infinity of c sub n times x power of n, and then the c sub n's are the coefficients of the series, and you can write it like this. Yes, it's going to be c0 plus c1 times x plus c2 times x squared, and so on. And yeah, power series centered at a. You could do a more general version. You could write the x as x minus a to power of n like that, and then you'll have the exact same series, but it's x minus a here. And the reason is when you plug in x equals to a, these all vanish. This goes to 0, this goes to 0, so all you're left with is the initial coefficient c sub 0. And the convention x minus a to power of 0 equals to 1 is chosen, is used even when x equals to a. So even when you have a minus a, which is 0 over 0, equals to 1. So then, so that the first term is always going to be just 1. That cancels out 1, so you're just left with the initial coefficient. Alright, let's keep going further. So remember the theorem also from earlier videos. So for a given power series like this, there are only 3 possibilities. The series converges for only when x equals to a, because when we plug in x equals to a here, these all vanish, you're just left with the initial one. Or the series converges for all x, or there is a positive number r such that the series converges if the absolute value of x minus a is less than r, and diverges if it's greater than r. And note that note that r is just the radius of convergence, and r equals to a for the first one. That would be the radius convergence of that, and r is equal to infinity for the second case for for all x. So this goes to infinity. And when absolute value of x minus a is equal to r instead of less than or greater, then the series may converge or may diverge, i.e. at the endpoints of the interval of convergence. X equals 2, x equals a plus or minus r, and here's just a visual representation of that. So convergence for x minus a, absolute value of x minus a is less than r, and like this, and then this is filled in for x equals a. X equals a, this is filled in because remember that's it's always converges for that. And when at the endpoints a plus r and a minus r, it's a open circle there, just so that because it may or may not diverge, or may or may not converge. And then beyond that radius of convergence, it's going to be divergence always. Anyways, go further to Taylor and Maclaurin series. Recall that Taylor series is just a power series in which the coefficients are determined from the function's derivatives. And here's the theorem: if f has a power series representation or expansion at a, so that's if you have a function equal to the power series, then its coefficients are given by this formula. And you have the, so this is the coefficient c sub n equals to the nth derivative at a divided by n factorial, and you could expand it out. Like this is just a Taylor series, so each one's a derivative at a, the second derivative, third derivative, etc. And the Maclaurin series is just a specific type of Taylor series with a equals to 0, so this is the nth derivative at 0. Then the first one's going to be f of 0 plus f prime of 0, so derivative at 0, the second derivative at 0, etc., and then just your usual power series. So now a quick recap on the binomial theorem. So the binomial theorem or binomial expansion is the algebraic expansion of the powers of a binomial, that is a polynomial consisting of just 2 terms or 2 monomials. So yes, if it's 1 term, that's a monomial, 2 terms a binomial, and general is a polynomial. So there's x plus y. So if you x plus y to the power 4, for example, you get this, you get x to the power 4 plus y times x to the power 3, and then y1, and then this goes 6, this is x squared, y squared. Notice the powers of x goes from 4 all the way to 1, all the way to 0, it vanishes there. And then the y's goes from 1 all the way to 4 and vanishes. And then, it just goes from y0, y to the power of 0 is 1, and then it goes to 4. And then you could write it like this in general, so x plus y to the power of n, you have it write it in these binomial coefficients, n choose 0, n choose 1, n choose 2, etc. And then the x power of n goes all the way to x power of 0, and y power of 0 goes all the way to y power of n. And also here, then you can write this in summation format, x plus y power of n equals to n choose, summation from k equals 0 to n of n choose k, and you have it write this, x power of n minus k, and then y power of k. So this means that when k is 0, so this is y0, But then when k is 0, n minus 0 is just n, so that's this part. But you could also reverse these. You could go x power of k times n times y to the power of n, y to the power of n minus k. Because then in this case you just start from this side. You just start from here, x to 0, and then y to the power of n, and then you just go backwards. So you could write it as in either or. And the term n over k, like this in brackets, are the binomial coefficients, and often pronounced quote n choose k. So this right here. They can be determined in factorial form or via Pascal's triangle, in which each term is a sum of the two above it. So you have n choose k. You could write this as n factorial over k factorial times n minus k factorial. And here's Pascal's triangle. Start from 1 and you add up the ones above it. So 1 plus 1 is 2. You have 1 plus 2 is 3, etc. And then for the n equals to 4, so over here, we have 1, 4, 6, 4, 1. In other words, if we keep doing this Pascal's triangle, so 1 plus 3 is 4, 1 plus 0 is 1, so we get this 1, 4, 6, 4, yeah, etc. So 3 plus 1 is 4, 3 plus 3 is 6. So yeah, we just sum them up and we get this n equals 4 over this one. Anyways, now that we've got over that one, let's jump further now to the binomial series. So recall that the binomial series is just a Maclaurin series for the function 1 plus x to the power of k. Yeah, so this is similar to the binomial theorem, but now this k, and also we chose y is equal to 1, as opposed to, this one's just x plus y, so we have y equals to 1. And k is any real number, it's not just a integer. Because remember, this one is just an integer. So this is 4, this is, these are integers, 1, 2, 0, 1, 2, 3, 4, etc. So yeah, that's the integer. This one is any real number. So in my earlier video, I went over the derivation of the binomial series and used the ratio test to determine that its interval of convergence is absolute value of x is less than 1. Yeah, so that's the interval of convergence, or you could write radius of convergence and so on. Because in this case, a equals 0 for Maclaurin series. So anyways, here is just a screenshot from the calculus book, but here's from my earlier video. So find a Maclaurin series for f of x equals to 1 plus x power of k, where k is any real number. So just taking the derivatives, and then you get this pattern like that. And then, yeah, just similar to the binomial theorem pattern, the factorial. And then therefore, and once you get this pattern, so this is going to be the nth derivative at 0, at x equals a equals 0. So you get k minus 1, and then all the way to k minus n plus 1. And then therefore the Maclaurin series for f of x equals to 1 plus x power of k is this. There's our binomial series. This series is called the binomial series, and if its nth term is an, so this one right here, and using the ratio test to divide an plus 1 divided by an, the absolute value, you eventually get to this term. Then when you take the derivative, as n approaches infinity, it goes to x. So the ratio test gives the absolute value of x. Thus, by the ratio test, the binomial series converges if absolute value of x is less than 1, and diverges if absolute value of x is greater than 1. And also further, the following theorem states that 1 plus x power of k is equal to the sum of its Maclaurin series, and I've proved it in exercise 3 in that video. Anyway, so we get the binomial series right here. So this equals to, so if k is any real number and absolute value of x is less than 1, then we get 1 plus x to the power of k equals to this binomial series. It's going further. So convergence at the endpoints. This is for the radius of convergence is 1. Yeah, it's just going to be equal to 1. But the convergence at the endpoints depends on the value of k. So although the binomial series converges for absolute value of x is less than 1, the question of whether or not it converges at the endpoints plus or minus 1 depends on the value of k. And it turns out that the series converges at 1 if k is greater than negative 1 and less than or equal to 0. And at both endpoints if k is greater than or equal to 0. Notice that if k is a positive integer and n greater than k, then the expression k choose n contains a factor k minus k. So k choose n equals 0 for n is greater than k. This means that the series terminates and reduces to the ordinary binomial theorem when k is a positive integer. MES noted reduces to the ordinary binomial theorem with y equals 1. Remember, x plus y to the power of n was the binomial theorem. So yes, anyway, so when just wrote this down. So when n is greater than k or both positive integers, we have k choose n like this. So that's going to be 1 over n factorial, then k times k minus 1, k minus 2, etc. then all the way to k minus n minus 1. Because remember how these powers are. So this is k minus 2, this is 3 factorial. This is k minus 1, this is 2 factorial. So when you're subtracting 1, you're going to have to, if you're subtracting minus 3, you have to add another plus 1 to it. Or you could view it as n minus 1. So 3 minus 1 is 2, so you're subtracting it like this. So k minus n minus 1, or which is the same thing, negative 1 plus 1. Like that. And then at this point, you're going to have a k minus k because n is greater than k. So you're eventually going to have a point where you're going to go k minus 1, 2, 3, all the way to k minus k. And then you're going to keep going until you get k minus n plus 1. So in other words, this just cancels. So for all of them, they just terminate equals to 0. And all you're left with is, well, everything beyond everything beyond k choose k is equal to 0. And then you just get our usual binomial theorem over here. Yeah, which is just 1 plus kx and then plus k minus 1, 2 factorial, etc. Keeps going on and on. And then it just terminates at this point here, 1 plus x power of k. And remember, y is equal to 1. So the whole time y is whatever y power of anything is just 1. So that's why I remove that there. And also important note on the binomial coefficients. So the binomial series is defined for when k is any real number. And thus the binomial coefficients are written in a more general version below. So here's the traditional notation k choose n equals to k and then k minus 1, k minus 2, etc. all the way to k minus n plus 1. So this is if n is, for example, 10, this is going to be 9, so minus 9. So that's why we have the plus 1. And these numbers are called the binomial coefficients. But if k is a positive integer, where k is greater than n, then it is equivalent to the usual factorial form present in the binomial theorem. So remember this formula right here, k factorial over n factorial k minus n factorial. This is for k choose n. We just have it reversed. You could just go factorial. This just equals to k times, where k is greater than n. So k times, k times k minus 1 times k minus 2, etc. all the way up to, this one is just before the last one. So you have k minus n minus 1 all the way to k minus n factorial. So this is just using factorial rules. And at the bottom number was k minus n factorial. So these would cancel with this. And you're just left with, this is the traditional format. So note also that the terminology for the binomial coefficient is usually reversed for considering the binomial series versus a binomial theorem. And here's binomial series written like this, just because you have a summation from n equals 0 there already, the n's already used. So then you're just going to go k choose n. So this is the one that's incrementing, that's one that's fixed, and then times x power of n, like that. And the binomial theorem is usually written like n choose k. So notice how it's k choose n is n choose k. So you just have it reversed. And again, it's because n is usually the term that's used for incrementing an integer. So x plus y is power of n. So we just choose that, as opposed to the k. K is chosen here because n is chosen for the summation. So anyways, just wanted to get that out of the way. So now let's look at convergence of the binomial series. Alright, so now that we finally got here, let's put this is ... like that. I usually put them here because when I upload to Hive in article format, this is considered a new line, like a new section. It makes it a full line across. Anyways, you can spot that when you look at the notes. Alright, so I'll be using the following PDF for the proof of the convergence at the endpoints for the binomial series. It is by mathematics professor John Laboute from McGill University in Montreal, Quebec, Canada. Let me just note, unlike the very well-written paper by Esther Fix, this particular lecture PDF by John Laboute was painfully hard to follow, and much of the proof was skipped through. It's absolutely painful. Anyways, so here's a link to it. There's an archive, and here's a local archive in case anything happens to the website. So anyways, so Math 255, Lecture 222, Lecture 22, Power Series, the binomial series. Let me just note, I'll be using the term k instead of the term alpha, it's a Greek letter alpha, term used in the PDF lecture. So just because we've been using it before, so it's more, I'm more familiar with this one for the binomial series. So the binomial series is the Maclaurin power series for the function f of x equals to 1 plus x power of k and is equal to f of x. That is, and you're just writing it all out for reference again. Alright, so this is the part where I'm going to start writing stuff. So we have, this is, again, we know that this is equal to, and starting from n equals 0, and I'm just going to write this all out. And this is going to be k minus 1, and then k minus 2, and then ... all the way to k minus n plus 1. like that. And this is going to be n factorial. And then we have x to the power of n. Alright, and now let's go over the ratio test again for completeness, just to get it all in this video, because we're dealing with convergence. To determine the radius of convergence, remember ratio test, and I have it ingrained into my brain right now. So it's just going to be an plus 1, and then we're going to take the limit afterwards of it. So here is going to be like this. This equals 2, and then we're going to write the factorials like this. This is going to be for the n plus 1, so it's going to be k minus 1 all the way k minus 2, and then dot dot dot. Then this one is, it's going to be one term after this one, so we're going to include this k minus n plus 1, and then the next one is going to be k minus then we're going to add another one, so it's going to be k minus n, like that. And again, this is because, put it like that. Yeah, this part right here, if you look at this one here, that's n. So when you plug in n plus 1 inside there, you're gonna get a k minus an n plus 1 plus 1. So then this would be minus n plus then minus 1. Yeah, k minus 1. Yeah, minus n minus 1 plus 1. So these just cancel. And we're just left with that over there. So this is going to be x to the n plus 1. I'll divide this by a n, and this is, yeah, I'll divide this by n plus 1 factorial. And now we're going to be multiplying this by, well, dividing by this one, so we're just going to do the upside down of the, we're just going to put this upside down. So this is going to be, on the bottom, there's going to be these the k's and the x power of n, and then the top's going to be n factorial. This is going to be just inverse of this, n factorial, and then this is going to be like that, and we're going to be multiplying this all the way by k minus 1 dot 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 all the way to the regular k minus n plus 1, like that, and then x power of n, like that. And yeah, this is all absolute value. Let's put it like that. Now this, what happens here is all this terms cancel. These are all this one. That's the same exact thing. And then this part right here, this is x power of n plus 1, and then divided by x power of n. Use our power laws, that's going to subtract. So we can actually cancel these out. Then we're just going to be left with x to the power of 1. Write this a bit better. This is going to be x, like that. And then the next one here, this one, recall, is using factorial rules. This is the same thing as writing n plus 1 times it by n factorial. So in other words, this would cancel with this. So again, all you're left with is this k minus n. So absolute value of k minus n over n plus 1, like that, and then times it by x. Yeah, this is all we are left with, times it by x. And now you could write this as equaling to, well, the only thing I could be positive, or the only thing I could be negative is this k minus n or this x. This n plus 1 is always positive. So this can be absolute value of k minus n, and then divide this by n plus 1, and then times it by x, absolute value of x, like that. And thus, the limit, so thus, limit as n approaches infinity of, now the ratio, I'll just put this for completeness, and n plus 1 over an equals to limit as n approaches infinity of absolute value of k minus n over n plus 1 times by absolute value of x. And the x is, yeah, it's not, this limit is in terms of n, so this doesn't affect it, so we can just factor that out, as it's going to be absolute value of x. They factor out of the limit, absolute value of x, times it by the limit as n approaches infinity, and then we have over here, and I'll just put this all in a big bracket like that, just so it could be easier to work with, and absolute value of n plus 1. Yeah, absolute value of k minus n divided by n plus 1. And I'm gonna multiply the top and bottom by the highest power, which is n. So we're gonna do the usual format, so like this, 1 over n over 1 over n, like that. And what we end up having is, as usual, limits, working with limits. So this will cancel. Yes, I mean, this will be k over n. I'll just write this fully again. This equals to, so this equals to absolute value of x times by limit n approaches infinity, and then we're going to have k over n, and then minus 1, like that. Then divide this by absolute value divided by 1, so n over n is 1, and then plus 1 over n, like that. And now as n goes to infinity, I'll write this n a bit better. Looks like an h. So right like that. This is going to be 1 over infinity goes to 0. This goes to 1 over infinity goes to 0. So in other words, we're going to have a negative 1 over 1. So this equals to absolute value of x times by negative 1 over 1. Absolute value of it. So that just equals to 1. So this just equals to absolute value of x, like that. So as we saw in an earlier video in that screenshot. So yeah, so the limit goes to absolute value of x. Alright, so thus by the ratio test, the binomial series converges if absolute value of x is less than 1, and diverges if absolute value of x is greater than 1. So yeah, so remember when limit the ratio test, if it equals to if it equals to L, which is greater than 1, it diverges. If it's less than 1, it is convergent. Like that. Endpoint x equals to negative 1 using Raabe's test converges when k is greater than 0 and diverges when k is less than 0. So when x is equal to negative 1 or plus 1, the ratio test is equal to 1 and is thus inconclusive. So recall, or let's put it like this. So at x equals to plus or minus 1, what we end up having is, so either or, but in this case we're going to be looking at x equals to negative 1, but in either case, when x equals to plus or minus 1, we get the limit as n approaches infinity. I'm just doing this for completeness. This is going to be an plus 1, this is for the ratio test, an, this equals to, again remember this just equals to absolute value of x, like that, and this is going to equal to plus or minus 1, which equals to 1. Alright, so now this is where we can use Raabe's test. So that's why I went over the Kummer and Raabe's test discussed earlier and shown below for the Raabe's test. So here's a screenshot from the from Sarah Fix's paper. So theorem 8. So Raabe's test let summation from n equals 1 to infinity of an be a series with positive terms, and assume that rho is equal to limit as n approaches infinity of n times an divided by an plus 1 minus 1, and that exists, i.e. finite. Then if rho is greater than 1, then the series converges. If rho is less than 1, then the series diverges, and if rho is equal to 1, then this one may either converge or diverge, and the test is inconclusive. Yeah, so now in our case, when x is equal to negative 1 and we have n is greater than k, the sequence has a constant sign, thus we can apply Raabe's test. And what I mean by that is because if we scroll up over to here, this is because we're going to have a negative 1 there, and then this is going to be this x is going to be alternating from negative 1 to positive 1 depending on if the power is odd or even. But when it's greater than when n is greater than k, you're going to eventually have the same constant sign. And what I mean by that is, let's just look at this right here. So let's make a table. So for n is greater than k, we get here, I'm going to write, let's say n, and let's say it's odd. Because remember, this one is for all, this is for positive terms, but ours is, all that matters is actually it's just a constant sign. So if it's all negatives, it's fine, because you could factor out a negative to get all positive terms. So we have, if n is odd, and let's say we have our sequence an, or the terms are going to be an, which equals to k choose n, and then we have x to the power of n, which is going to be in our case negative 1 to the power of n. So remember, this negative 1 is going to be alternating. This particular term is going to be alternating, and then we're going to have, so the first one is going to be, well, 1 over n factorial times by k, and then k minus 1, and then dot 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 all the way to k minus n plus 1. So this is going to be, so if n is greater than k, this part right here may be less than it. So we're just going to include this all in the term. This could be plus or minus, depending on the value of k. If k is positive everywhere, you're still going to have, so this is going to be a positive term, this is going to be a negative term, this is going to be negative there. It's going to be, it's going to be alternating plus or minus signs. So we'll just write plus or minus because we don't know which one it is. And then the next one's going to be negative 1 to the power of n, which is odd. So this is going to be negative. Because, yeah, this is going to be equal to negative because this is odd. So, yeah, negative 1 to the power of 3 is going to be odd. It's going to be negative 1, etc. If negative 1 to the power of 1, it's going to be negative 1, and so on. So sine, so I'll put it all the way across here because we may need more space. So sine is going to be plus or minus, and then minus. Yeah, so that's going to be, so whatever that one is, plus or minus. And then the next one here is going to be, the next one's going to be n plus 1. So the next term after that is going to be n plus 1. This is going to be even. Because you're an odd plus another plus 1 is going to be even. So it's going to be even. And then our formula is going to be 1 plus n, 1 divided by n plus 1 factorial. Then we have our k minus 1, etc. all the way to dot, dot, dot. And then we're going to get this one right here, k minus n plus 1. And then we're going to go one more of that. So k minus n plus 1 minus 1. So k minus n, like that. And this one right here, we already know this is plus or minus. Plus or minus, so nothing changes. So it's always going to be plus or minus as above. So same one here, same one here. And then this one's going to be k minus n. Yeah, this is going to be negative. Because n is greater than k. So you're going to go k minus a larger number. So it's going to be negative. So whatever k is going to be, it doesn't matter what it is, it's going to be negative. So this will be negative. Let's put a negative sign like this. And then the next one's going to be negative 1 to the power of n plus 1. It's going to be even. So this is going to be negative. I mean, it's going to be positive. So in other words, all that matters is we're going to get the exact same thing as before as this one. So we're going to get plus or minus, and then we're going to get a minus. And then the next one is going to be the term after that, n plus 2, which is going to be odd. So we're going to have a 1 over n plus 2 factorial. Then we're going to have a usual k times k minus 1, dot, 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 all the way to k minus n plus 1. And we know this one right here is, again, plus or minus, as above, depending on which one it was. If it was plus, it's going to be plus, 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 plus. If it's a minus, it's going to be minus, minus, minus. And then this one here is going to, and then we're going to have this one, k minus n, which is, we know this is negative. So the one's always after is going to be negative. And then the next one's going to be k minus n minus 1, like that. Remember, we subtract 1 every single time when we're going further. And again, you could even look at the same formula, k minus n plus 1. If we plug in n plus 2 inside there, we're going to have a minus n, and then a minus 2 plus 1. So it's going to be minus 1. It's going to be negative 1, n plus 2. Yeah, so that's n plus 2. And this one here is going to be always negative because n is greater than k. And then negative n minus 1 is also going to be, the absolute value is greater than k. So anyway, subtracting, this one's going to be odd. It's going to be negative, like that. So remember, this is plus or minus, and then the combination of these two is going to be plus. Because negative times negative is positive. So then we're just going to be left with, well, plus or minus, and then this negative sign again. Because all that matters is this, and this one here. So plus or minus, and minus. So these are all the exact same thing. So the same. So let's put a same sign. And yeah, so same signs, move it over to this side. And now if you keep going dot, 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 you're going to get the exact same thing. You're going to get a plus or minus, and then a minus. So whatever it is. If it's plus, it's going to be minus. If it's minus, it's going to be plus. It's going to be all positive. And again, all that matters is that they're the exact same constant sign. It's the same thing as, because then you can make it into positive terms by taking a negative out. And thus for, I'll spread it all right here. So thus, for n is greater than k, we're gonna have the absolute value like this. We're looking at the series from n equals to 1 of an. This will just equal to, so remember, all that matters is the point as we go into infinity. So we're going to have up to n. Let's go from I equals to 1 of an. So this is going to be finite. And if it's finite, it has a limit. And then you can have plus or minus. It doesn't matter how you do it. Yeah, you can just say plus, but you could also factor out the minus sign. Let's put a plus or minus. It doesn't matter how you can do it, just so you get a positive terms here. So you get infinity like that. I equals to n, so all the way to I equals n, and then an. So all that matters is this is what you test for convergence. So that's finite, that's a limit that exists, so this is going to be test for convergence. Convergence. So yes, it's plus or minus, but let's put a plus, because remember, if it's a minus, then you could just factor it out and put an absolute value sign. And also, if we just write and, because remember, it doesn't matter if it's what sign it is. And if we look at over here, so remember, these are all positive terms. For this one is as positive terms, and you have this ratio an divided by an plus 1. An, if they're the same sign, and these are all positive, this is the same thing as saying equals to plus or minus absolute value of an over plus or minus absolute value of an plus 1. And then this equals to, well, just absolute value of an over an plus 1. So in other words, an divided by an plus 1 is the same. We're going to get positive terms. So the ratio is always positive because the signs are the same. These would just cancel. Alright, so now that we got that out of the way, let's continue further. So applying Raabe's test and recalling the earlier derived ratio from the ratio test we have. Let's just scroll up to that ratio test we did. So we got up to this point right here. So we got absolute value of an plus 1 over an equals to k minus n divided by n plus 1 times x. So let's remove the absolute value sign. We'll just look at the internal over there. So k minus n. So let's just jump right here. So recall that an plus 1 over an is equal to k minus n over n plus 1 times x. And let's scroll up here. So yeah, we just remove the absolute value sign. So that's this part right here. Like that. So that's what we're looking at. Yeah, k minus n, that's this ratio an plus 1. Let's keep going further. And now for our case, we're going to be looking at x equals to negative 1, so then at the endpoint. So, yes, right, it's better. At x equals to negative 1, what we get is, so at x equals to negative 1, we get an plus 1 over an is equal to k minus n over n plus 1 times by negative 1, like that. Yeah, so we just plug in negative 1. And now this negative, we could just put that inside, so that the negative multiplied inside, so negative n is going to be positive, and then k is going to be negative. So we're going to have, and move it over to the other side, so n minus k over n plus 1, like this, and box this out. So that is our ratio, like that. But remember, the Raabe's test is the inverse of that. So we have an divided by an plus 1. So this is an. Yeah, so if we look at Raabe's test, it's an divided by an plus 1. So the inverse of the ratio test. So thus, just put it like this. Thus, our rho, let's call it rho, equals to limit as n approaches infinity of n times it by an over an plus 1 minus 1. So you can scroll up here. So that's this part right here. Yeah, rho, yeah, so limit as n times an divided by an plus 1 minus 1. And now we're going to inverse that. So we're going to equals to limit as n approaches infinity. And now we're going to have an n. And then this inverse of that, so we're going to have an n plus 1 on the top over n minus k, and then minus 1, like that. And now what I'll do is I'll multiply the n inside, so we're just going to do a bunch of algebra as per usual in mathematics. Mathematics should be just called algebra. Limit as n approaches infinity. And then multiply this n inside. Every single thing is going to be now n squared plus n, so the n multiplied inside there. Divide this by n over k, n minus k, then minus n, like that. And now we want the same common denominator, so we, as per usual, multiply this top and bottom by n minus k over n minus k. And then we can combine these together. So this equals to limit as n approaches infinity, like this. And then we get n squared yeah, so n squared plus n, and all the same common denominator, so minus, and then this n times n is going to be n squared, and negative n times negative k is going to be plus nk. Divide this by n over k like that. And now what we get is, well, this cancels with this, like that. And all we're left with now is, so erase this. Yes, yeah, what we're left with now is limit as n approaches infinity of, now we get a n plus nk over n k like that. And then as per usual, because we don't need this bracket anymore, so we could ignore this bracket as well because it's all just one fraction. So we have that. I'm going to move these both to the left. Alright, so move it over to the left. So now this one, as per usual, multiply the top and bottom by the division of the power. Well, divide both sides by 1 over n, the highest power. And then this would, what this would happen is equals to limit as n approaches infinity. And now this cancels, so we're going to have, this cancels will be 1 plus k. Yeah, so 1 plus k is on the top, and at the bottom we're going to have a 1, so 1 divided by n divided by n is 1, minus k over n. And then as you go into infinity, this is the only thing that matters, is going to be 1 over infinity goes to 0. So this equals to a, yes, this is going to be equal to 1 plus k. This goes to 0. And this goes to 0, so we have 1 plus k divided by 1, so this equals to 1 plus k. In other words, we have rho is equal to 1 plus k. So, and we know our Raabe's test, scroll up Raabe's test. So when rho is greater than 1, the series converges, and when rho is less than 1, the series diverges. So in other words, so when, yeah, right here, so when, yeah, just fill that in. So when rho is greater than 1, what we end up having is 1 plus k is greater than 1, so move this 1 over to the other side. And then we get, well, they just cancel, so we're just going to be left with k greater than 0. So this is convergence. So this is convergence. Or just say converges. So it converges, and then when rho is less than 1 by Raabe's test, we have 1 plus k less than 1, and then move this over as per usual. This is just going to cancel. We're going to have k less than 0 is going to be divergence, or diverges. Or better yet, I'll just unbox that and then box these two together, like that. So yes, there we've got the convergence now for the endpoint x equals -1. It's just fascinating stuff. So thus at the endpoint x equals -1, the binomial series converges when k is greater than 0 and diverges when k is less than 0. And now let's look at the endpoint, the second endpoint, k is equal to 1. And this is an alternating series. And I'll show that here. So if x equals to 1, the binomial series becomes alternating for n is greater than k. So same as before we had our table. So for n is greater than k, because remember all that matters is as n approaches infinity, not any finite amount of n. So we're going to have it like this, make a table. So let's say we have n. And now this doesn't matter here if this is a positive or if this is odd or not. In the other one, if we started off with an even one, this would be a plus. So this would be -1 power of an even n. So it's going to be plus plus plus. So it's going to be plus 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 times it by plus or minus. And this in this case here, it does not matter because, as I'll show, so we have an is equal to k factorial k over n. I mean, yeah, k over n, or k choose n. Like that. Yeah, k choose n and then x to the power of n, but in this case x is 1 to the power of n. So this is always going to be equal to 1. So we could actually simplify this further. This just equals to kn. So whatever n is always going to be 1. So this equals to, yeah, times 1. So that just equals to that. And I'm going to put a sign here. We might need more space, so sign. Alright, yeah, so that's just going to be positive there. Let's move this line further. So now we're going to have the first one for n. It's going to be 1 over n factorial. And we're going to have our usual k minus 1, and then dot dot dot, all the way to k minus n plus 1, like that. And this is going to be, well, plus or minus. So it's going to be plus or minus. And then the next one is, well, we know that it's going to be 1 power of n. This is just positive. It's always going to be positive. So it doesn't matter there. So we're just going to put the sign here, plus or minus, like that. Now the next one is going to be n plus 1. Yeah, so n plus 1 like this. And now it's going to be, well, 1 over n plus 1 factorial. This doesn't change the sign. It's always positive. We're going to have a k minus 1 dot 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 k minus n plus 1. And the next one's going to be k minus, this is going to be bigger than that, yeah. Yeah, plus 1, and then the next one's going to be n, yeah, k minus n. Like this. And now the difference here is, well, this one is plus or minus. This just depends on whatever we had initially, the sign. Now this one here is always going to be negative because n is greater than k, so k minus a larger number is going to be negative. So now what we get here is going to be plus or minus, and then times it by negative. And now the next one, yeah, the next one's going to be over here n plus 2. So at n plus 1, n plus 2 is going to be n plus 2 factorial, times it by, and then it's going to be the usual k minus 1 dot 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 k minus n plus 1. And this is going to be plus or minus, as per always. So plus or minus, and then the next one's going to be k minus n, which is negative. And then we're going to have k minus n minus 1, which is also negative. So this is going to be negative, but then these become positive, because 2 negatives becomes positive, so that becomes positive, and there's no other alternating 1 term. So this one here, the same thing as before, negative becomes positive, but then this becomes negative 1. Then that becomes the same sign, negative. But since that's always positive, there's no second cancellation. So this becomes plus or minus, and then it's going to be, then this is going to be plus now. Yeah, so this is going to be minus, plus, and then next one is going to be, well, at n plus 2, and n plus 3, it's going to be the exact same thing. So at n plus 3, make this bigger. Yeah, at n plus 3, we're going to have, let's write this down, 1 over n plus 3, just for completeness. And then this is going to be times it by k, k minus 1, the usual k minus n plus 1. This is going to be plus or minus, whatever we had started off with. Now it's going to be k minus n, and then k minus n minus 1, and then k minus, yeah, actually we need more space, so all I'll do is just remove this, k minus n like that. K minus 1, just remove that, just move it over to the left, and just put it the dot 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 here. Alright, so just get some space there. So now we're gonna have, yeah, so k times k times k minus 1, k minus 2, etc. all the way there. That's plus or minus 1. Minus, yeah, there's a plus or minus. And this is gonna be minus. So this minus becomes a plus, so those just cancel. And now we're having another one, n minus 2. Minus. So in other words, this becomes positive there, that doesn't change anything. So now it's going to be again plus or minus, and then minus. And then next one's going to be, well, it's going to add another negative, becomes positive. So in other words, we're going to go negative there, plus negative, and the next one, dot, 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 it's going to be plus or minus, and then plus. And then etc. So it keeps going on and on. So alternating. Alternating sign. Alright, so now that we have this, although it's alternating signs and we have an alternating series, we nonetheless can use the Raabe's test for absolute convergence. So using Raabe's test, absolute convergence when k is greater than 0. So since the series is an alternating series, we can nonetheless consider absolute convergence using Raabe's test. Because remember the earlier theorem of it's absolutely converges, it also converges. So yes, let's consider absolute value of an. So let's look at that absolute convergence. And also recall from the ratio test again. So recall the absolute value of an plus 1 over an. This equals 2. Let's just scroll up to that again. we recalled it here. An plus 1 is just equals to, divided by an equals to k minus n divided by n plus 1 x. And you can see that right here in the alternating series. So that is right here. So k minus n, then divided by n plus 1 times x, like that. And yeah, so you could either look at that over there. So anyways, we're looking at absolute convergence. So this equals to, again, we know this. Yeah, this equals to, and then we're going to write k minus n over n plus 1, like that. Again, just to confirm that, double check again. So yeah, k minus n and then n plus 1, like that. And there's the x times by x, like that. And then and then right here at x equals to 1, we get absolute value of k minus n, like that, n plus 1. All right, now that we have this, now note that when we have n is greater than k, because remember all that matters is as we're approaching infinity, so not a finite number of terms. So yeah, so we're going to look at this. So so when n is greater than k, then we could write this as an plus 1 over an is equal to, this just equals to, if this is absolute value, we could just write this as n, we can remove the absolute value, we could write n minus k and n plus 1, like that. Yeah, because n is greater than k, so it's always going to be positive. And now this right here, this is the same as for the endpoint x equals to -1. Because if you scroll up to the endpoint, the other one here, so this is at x equals to -1, we show that an plus 1 divided by an equals to, well, n minus k divided by n plus 1 is the exact same thing. So we could throw this inside, but now we're looking for absolute convergence, so all the terms an, the absolute value of an. So we're going to throw this inside over there, exactly the same as we would, but now we're looking at absolute convergence, and then we're gonna get the exact same answer. So we're gonna get the exact same thing as this. Throw this inside here, and this becomes rho is equal to 1 plus k, but it's for the absolute value of an. So thus we get, let's write thus rho is equal to, and just for completeness, this is right the absolute value sign. So we're looking for absolute convergence. So limit as n approaches infinity of n, and then we have this an over an plus 1, and it's the inverse of this. Remember, it's the inverse of that, and then minus 1. So if it's the inverse, I'll just remove this arrow. Exactly. So you throw that in there, but the inverse of it. So it's going to be n plus 1. Just because, yeah, so it's, yeah, throw that inside here, but now we're looking at absolute values of it for the, just only the positive terms. So absolute value of that, and this just equals to 1 plus k. Yeah, so let's just box this out, and then we can look at convergence. So when rho is greater than 1, we get k plus 1 is greater than 1, move this over, and then this just means that k is when, yeah, this cancels, so k is greater than 0, and series converges. So binomial series, the absolute value of it converges. Like that. Alright, yeah, so thus by Raabe's test, at the endpoint x equals 1, the binomial series absolutely converges, because we're looking at the absolute values of an, and therefore converges when k is greater than 0. So now using alternating series test, converges when k is between 0 and -1. Note that we can't use the Raabe's test to check for divergence of the alternating series, since absolute divergence does not necessarily mean divergence. Yeah, so we can't just say that if rho is less than 1, then k is less than 0 diverges, because that's absolute divergence. So yeah, so actually for completeness, let's just write this, make this a bit bigger here. Right, absolutely diverges, converges. Absolutely, just so that we don't get confused. So when rho is greater than, less than 1, we can't have it then k will be less than 0, we can't say absolutely diverges because it may conditionally converge, even though it absolutely diverges. Yeah, so right here, so we can't use Raabe's test to check for divergence of the alternating series, since absolute divergence does not necessarily mean divergence. And this is where we can apply the alternating series test from my earlier video. Yeah, from my earlier video, and here's a link to the Hive notes as well, and here is a screenshot from the calculus book. So the alternating series test: if the alternating series summation from n equals 1 to infinity of negative 1 to the power of n minus 1 bn equals to just something like this, b1 minus b2 plus b3 minus b4 plus b5, etc., where bn is positive terms, just to show that it's alternating there. So plus minus plus minus plus minus, where bn is greater than 0, satisfies these two conditions. Condition 1, or I, where bn plus 1 is less than or equal to bn for all n. In other words, it's decreasing. I mean, it's decreasing. So bn plus 1, each further term is decreasing, smaller than the previous one. And also, the second condition, the limit as n approaches infinity of bn is equal to 0. So the limit's going to 0, and that each term is decreasing. Decreasing, or it's the same. Then the series is convergent, and if it's the same, it's usually 0. Thus, in our case, then it's the convergent in that case. So thus, in our case, at the endpoint x equals 1, and when n is greater than k, the series is alternating, and we need to determine convergence when k is less than 0. Yeah, because we already solved that it converges when k is greater than 0, so now let's look at when k is less than 0, so we get some negative signs. And it says, again, at the endpoint x equals 1, and when n is greater than k, that's when the series becomes alternating, because all that matters is approaching to infinity. So now let's look at when when k is greater than negative 1 and less than 0, then what we have is, well, first off, let's recall for the ratio from the ratio test again. Recall that absolute value of an plus 1 over an is equal to this one, n minus k divided by n plus 1 for this is from over here. This is at x equals to 1, and I'll just say so this is for x equals to 1, and or actually just remove that, put for n is greater than k, and this is at let's put it at, how should I do this here? Put it at x equals to 1. Or I just moved it over here, so for, this is at x equals to 1. Let's put in bracket over there, and again, that's exactly just this point. Yeah, that is just over here. So at x equals 1, I have absolute value of k minus n, but then it becomes, when n is greater than k, we have n minus k, divided by n plus 1. So we're starting off from there, and now notice that for when n is negative, when k is negative, for k is less than 0, then k is just equal to negative absolute value of k. So that's all this means is just going to be negative sign. So if a negative sign and an absolute value. So thus, the absolute value of this, absolute value of an plus 1 over an, is equal to n minus, and then so this one here, minus a negative absolute value of k, like that, and this is going to be n plus 1. In other words, the negatives cancel. This just equals to n plus absolute value of k over n plus 1. And the absolute value of k, well, this is going to be less than if we had n plus 1. If we just replaced less than when k goes to 1, because this could be bigger than 1. Yeah. Actually, not bigger than 1. It's because k is between negative 1 and 1. So this is going to be less than n plus 1 plus 1, which equals to 1. And this is because k is less than 0, less than negative 1. Thus, absolute value of k is going to be less than 1. So in other words, if it's less than 1, the absolute value of it, then we're going to have this is going to be less than if this was just equal to 1. So n plus 1 is going to be less than... so n plus absolute value of k is going to be less than n plus 1 over there. Thus, these just cancel. And equals to 1. So in other words, what we have is absolute value of n plus 1 over an is less than 1. So now we can just move this over to this side. So what happens then is like that, what happens is, we get absolute value of an plus 1 is less than an. So this is the first condition. So this right here satisfies, or actually box the whole thing out. So satisfies condition I. Put this like this. And box this whole thing. And remember, condition I is just over here. So bn plus 1 is less than or equal to 1. And in our case, it's going to be, it's going to be absolute value of an plus 1. Is less than absolute value of an. Because remember, those are the positive terms of it, and we're including the negatives. So there's just going to be alternating signs, and this is looking at the absolute value of that part. So the absolute value is going to be decreasing. So this is the same thing as saying the absolute values are decreasing. So absolute values of the terms, but they're alternating, and then it's going to be decreasing. And for all n, in our case, for all n is greater than k. For all n is greater than k, because that's all that matters, is when it goes to infinity. So thus the first condition, an, absolute value of an plus 1 is less than an, of the alternating series test is satisfied. So we only have to show an approaches 0, or absolute value of an approaches 0, either or. If it's positive approaching 0 or negative, the same thing. So we have to show this right here, limit as n approaches infinity of limit bn approaches 0, and we'll just put it here just for completeness. So either or, if this goes to it, or we could put it like this. Absolute value or not. Actually, just leave it like that, because if it's just the even if it's alternating, the signs going to 0, it's the same thing as the absolute value is going to 0. So we just have to show this right here. And now if I write this out, limit as n approaches infinity of absolute value of an. Actually here just added the absolute value sign here. So show that absolute value of an approaches 0, and hence the same thing as an approaches 0. So this equals to limit as n approaches infinity, and now we know our so if we were trying to solve the limit of this one, it's not too obvious how to do it. So I'm just going to write this as, this is going to be k minus 1, and then this is going to be k minus 2, etc. And this is going to go all the way to dot dot dot. We're going to have k minus n plus 1, and then at x equals to 1, we're going to have a 1 power of n, like that. So it's not too obvious how to go about this one. And also this is going to be n factorial at the bottom, or you could write this as 1 times 2. This is how I was going about trying to think about how to solve this. And all the way to times by n, like that. So to see if this diverges or not, this is hard to tell if it converges to 0. So I just expanded like that, and it is not clear how to determine the limit of this function, but we can try converting this factorial multiplication into a logarithmic summation. Notice how these just line up like that. That's how they would line up, which often simplifies the equation using the logarithmic laws that I covered in one of my earliest videos. So if we could take the logarithmic of this, and take the limit of the logarithmic of this one, we could convert this multiplication into summation. So we can convert factorial multiplication into logarithmic summation. So recall my earlier video. So log laws of x and y are positive numbers. Then log of base a, x times y, equals to log a x plus log base a y. And you also, the division is going to be subtraction, and then you can take the power out like that. Thus, taking the limit of the natural of the bracket natural logarithmic of the sequence an, we get, or actually absolute value. Let's do everything absolute value. Make this bold. We get, so let's just take the limit of the natural log of it, just because usually dealing with natural logs, the same thing, just base e. So thus what we get is limit as n approaches infinity of now ln of absolute value of an, like that. So we get it's positive numbers inside. Now the limit of this one all in there. This equals to, so this equals to limit as n approaches infinity, and now we have the ln. If we take the ln of this, we can convert this entire multiplication, and this one just goes to 0. I mean, this just goes to 1. 1 power of n is always going to be 1. And now we have it, these all lined up. I'm going to write these all together as a summation, logarithmic summation. So that's why I had written that like that. So we're going to have it as ln k over 1 plus ln, just using the log law, so all these multiplications become this one here. And if you have x times y times z, same thing. Then you can just use this over and over again. So you'll have xy plus z, then you have x, then you separate xy. This is going to be ln k minus 1 over 2. And keep going on and on. Let's see the next one. The next one's going to be k minus 2 like that, and over 3. And then let's just do, let's ignore that. Let's go dot, dot, dot. And then the last one's going to be over here, k minus n plus 1, and then divided by n. And this is absolute value, so everything's absolute value. So ln of k minus n plus 1 over n, like that. So, and then it keeps going on, plus dot, dot, dot. It goes to infinity. Yeah, so now what this equals to as well, this just equals to this is just a summation going to infinity. So we could write that as a series. This is just a series, so limit as n approaches infinity. The same thing as writing, this goes from n equals to 1 up to infinity. And now we're going to write this ln, so the general term is this one right here. So ln of absolute value of k minus n plus 1 all over n, like that. And now this equals 2, and yeah, if we just divide this n inside, we get, this is summation up to infinity, n equals to 1. So we get the limit as a natural, the limit of the natural log of absolute value of an is equal to the series of natural logs. So that's absolutely fascinating stuff. So now this equals 2, and just divide this n inside, and also I'll just write this as k plus 1 over n, so that move this over to it, and then just so we can subtract negative n divided by n is equal to 1. So minus 1, like that. And now this equals 2. Well, before I get to that, well, we know that we're looking at the case k is less than 0, less than 1, or else write 4. Yeah, so for k is less than, it's going to be the absolute value of k is going to be less than 1. So in other words, k is between negative 1 and 0. That means, thus we have k plus 1 is going to be, you can just add a plus 1 to it. It's going to be less than 1 and greater than 0. So just add a plus to it. Or instead of saying 4, I'll just write 4 and thus. So we have that. So we could get rid of that absolute value sign, because this is less than 1. So you're dividing by numbers. Always going to be less than 1, because this is the top is less than 1. So in other words, less than 1 subtract by 1 is going to be negative. So we'll just reverse it. So thus, this is going to be always negative. So we're just going to reverse it. Equals to, reverse of 1 minus this number. So 1 minus a small number, less than 1. So we get rid of the bracket, the absolute value sign. So I'll just put this in bracket like this. And now on the left side here is going to be equal to, or I'll move it even further here, equals to summation up to infinity from n equals to 1 of ln, and now we're just going to get 1 minus k plus 1 over n, like that. Yeah, so just like that. And then move this over to this side just to get some more space, and we could move this back to where it belongs, right in the center. Just one more time. And here. Yeah, so that's what we get. Yeah, so thus the limit of the natural log of the sequence absolute value of an right there is equal to the above series, which over here. So we get a limit of this natural log of this sequence is equal to this summation of this natural log, which is pretty amazing. Up to infinity, so a series. Hashtag interesting stuff. Interesting, yeah, that's spelled right. So note that the PDF lecture proof is not clear and skips most of their steps, so instead we will test for convergence or divergence of the series by the limit comparison test, also covered in my earlier video, so from a link below, same link as above. So limit comparison test, suppose that the series an and bn are series with positive terms if the limit as n approaches infinity of an divided by bn is equal to c, where c is a finite number and c is greater than 0, then either both series converge or both diverge. Yeah, so in other words, all we have to do is take a limit of a series divided by another series, and then so if we know one of them diverges or converges, and we get this c that's greater than 0 is a finite number, then the other one is the same as the one we're comparing it with. So it's a limit comparison test. So it's very fascinating stuff. So this one, I'm just gonna go out of the dictionary. So note that in our case, our logarithmic series is always less than 0, but or I remove this we, but this just means, and I'll show you why it's less than 0, this just means we have to ensure that bn is negative for all terms as well. Like before, all that matters is that the sign for each term is the same as n approaches infinity, so that we aren't dealing with an alternating series as n approaches infinity. So yes, even though here this logarithmic is always going to be negative, because this is 1 minus a number less than 1 divided by n, is always going to be, it's always going to be less than 1. And recall... So recall here. Yeah, recall the graph of ln. It's going to look like this. If this is x, this is y, and then recall this is 0. Yeah, so this is the graph. I'll do the graph of the natural log. It's going to look something like this. It goes to negative infinity at the bottom there. And this is the graph for y equals ln of x. And remember, this is the same thing as, or inverse, this is going to be y equals to x. So that's all of our natural logs are just an inverse function. So if e to the y equals x, then y is equal to ln x, like that. So that means at this point right here, at x is equal to 1, then y is 0. So e to the 0 is 1. And also just for reference, so here is at e, so when x is equal to e, y has to equal to 1, so e to the 1 equals to equals to e, like this. And here is replace both lines with just a light line like that. And now what we have is, in our case we have ln of, so that's this one above here, 1 minus k plus 1 over n. So 1 minus k plus 1 over n. Remember, k plus 1 is less than 1. Because number k is between 0 and negative 1, so then 0 and negative 1, between that, it's going to be less than, absolute value is less than 1, so plus 1. It's going to be a number smaller than 1 here divided by n. So this right here is just going to be less than 1. So if it's less than 1, if this is the x part, if it's less than 1, this whole thing becomes less than 0. So in other words, this just becomes, let's throw this over there. This becomes over here. So it's less than 0, like that. Yeah, so thus again, even though this is less than 0, and these are all positive terms, we just have to ensure that the series we're comparing with is always negative as well. So that's all that matters. Because you can always factor out, because remember, if this is always less than it, we just put a negative. And then test for convergence of that. So now these are all positive terms. So ln, like that. Alright, so now going further, so setting u just equals to k plus 1, just so we don't need to deal with this plus 1 all the time. And choosing bn equals to negative, because it's all negative, so the same signs. Is bn equals to negative u divided by n, so it's exactly over here. We can apply the limit comparison test. And remember, limit comparison test, you're just dividing by another one there. So we're going to select our b sub n as that. And what happens here is limit as n approaches infinity of, now our series is just going to be over here, 1 minus k plus 1 divided by n, or 1 minus u over n, so that's the ln. And so we're testing this series converges. So this equals to ln, so the terms inside, 1 minus u over n all over negative u over n. Now the issue here is, well, as n approaches infinity, we get a, this becomes a negative 1 over infinity, and this is approaching 0. Likewise here, we get a negative 1 over infinity, this is approaching 0. So we get a ln, yes, we get a negative ln 1 over, yes, this is approaching 0, it's going to be approaching ln 1, over negative 0. Or just negative 0 or negative whatever. These signs just cancel, and we're just going to be left with a ln. Number ln 1 is just 0. So we're having a 0 over 0, so this is indeterminate. Indeterminate, so we could apply L'Hopital's rule. Indeterminate, that should be spelled right. So what we could do is, thus what we could do is just write limit as n approaches infinity of ln 1 divided by 1 minus u divided by n over negative u over n. This equals to, and I put an h for L'Hopital's rule. L'Hopital's rule, spelled hospital. L'Hopital's rule, as referenced above. And now that we have this, now this equals to the limit as n approaches infinity. Let's put this a bit better. Now we're going to get a derivative d over dn of ln. This is going to be d over dn of ln 1 minus u over n over d over dn of negative u over n. And now this equals to, limit as n approaches infinity, and then ln, remember ln is just going to be 1 divided by. So you can write this as 1 divided by 1 minus u over n. And then using chain rule, times it by, the top's going to be, well, we have a negative there. Now negative u over n squared, and that's because we already know this, that d over dn of, well, negative u n, let's put negative u n, u times n, this is the same thing as negative 1. Yeah, and as before, we already did this derivative, this n negative goes down, so this equals to plus, so plus goes down, negative 1, u n minus 2. Yeah, so u n, and then this equals to, this is multiplication, u times n, and this becomes a u over n squared, like that. Just put a bracket, I'll just put a circle there. Divide this by, let's move this over, let's move it above. So now divided by this part here is the same thing as this one here. So we're just going to be divided by, and I forgot to cancel the sign, so then the negative signs cancel. Because remember, the negative 1 goes down, and now we're going to have the same thing here. This is going to be derivative of this one, same as the top one, so plus u n squared, and now this just cancels. So what we're left with is equals to limit as n approaches infinity of 1 over 1 minus u over n, and now this goes to, well, 1 over infinity is negative 1 over infinity, and it goes to 0 as n goes to infinity. So in other words, you get a 1. This equals to 1, which is, well, greater than c, which equals to c greater than 0, like that. Yeah, so now that we have this, so this limit of this these two ratios is equal to 1, which equals to, just our c is greater than 0, so that's just a finite number right here, so the limit an over bn. So now we just have to find out if our comparison series bn is convergent or divergent. So since the limit is finite and greater than 0, we now just need to determine the convergence of the series bn, which in our case is just a constant multiple of the harmonic p equals 1 series, which diverges. And we could see that over here, this is our bn, like this is 1 equals to negative u divided by n, where u is just a constant, which is k plus 1. So that's just going to be, now we're just going to have a negative 1 divided by n. Negative 1 divided by n, or just 1 divided by n is equal to the harmonic series. This means that our natural log series also diverges by the limit comparison test. So, and I'll write this down as well. So we have this limit equals to c, and where c is greater than 0, but the bn diverges. Thus, this is our series of the natural log right here. This diverges to negative infinity. And I'll get to that in a bit. So this means that our natural log series also diverges by the limit comparison test. Also note that the infinite series for bn, so a limit from n equals 1 of b sub n, this equals to the up to infinity from n equals to 1. Write the summation a bit more straight. This is of negative u over n. Now this equals 2, and take out the negative u, is just a constant. And that's not affected by the n variable, or the integer. N equals to 1, and now this becomes 1 over n. And yes, we have this, and this 1 over n, we already know that diverges. That's just the harmonic series, or p equals to 1 series, which we've covered several times, and it's ingrained into my brain. This always happens whenever I do these kind of videos. It just I make sure that everything's stuck in my brain forever because it's a lot of math. Anyway, so this is going to be negative u. This is going to be infinity. So this is just going towards a negative infinity. So this is the limits going towards negative infinity. I'll just put the circle both like that. Thus, what we have is thus by the limit comparison test, the top part as well, this an, is also going to go diverges to infinity, or negative infinity in our case, and because the sign is always negative. So this part right here, this is the an term. So thus we have, and write it down, so thus limit as n approaches infinity. Yeah, so limit as n approaches infinity of ln, and it's, let's just go back again, refresher. This is of this term, or just this whole starting point. So ln of an, the sequence. Yeah, go back here. So ln absolute value of an, which equals to the limit, or now it's just an infinite series, equals to, like this, infinity, up to from n equals to 1 of ln, and now we have ln of 1 minus k plus 1 over n. And where u, again, remember, u is just equal to, over here, u is equal to k plus 1, where we defined it as. And now this equals to, well, this diverges, but remember, all these are negative. Every single one of these terms are this ln of this one, because this k plus 1 divided by n is always less than 1. And also note that here we're starting at n equals 1, because if you put in n equals 0, this goes to infinity there, so I'm not defined for that. Yeah, but again, all that matters is that as approaching infinity, so you could just start from n equals, yeah, wherever. N equals 2 or 3 or 4, etc. Because that would be, yeah, the starting point, because you're going towards infinity, so it doesn't really matter. So anyways, now what we have is this equals to negative infinity, because all those terms are negative, and now we know it diverges, so thus they both diverge. This is by the limit comparison test. So thus, in our case, yeah, since the harmonic series diverges, and we know that this is the ln of this, then the series an also diverges, and it's going to be negative. All right, and now this implies, well, which implies, or let's put it like this. Yeah, which implies, put an arrow there, which implies that an approaches 0. And can you see why this is? Remember, this is ln of absolute value of an, or ln of right here, of this term right here. And this is going to negative infinity. Now, if we look at our graph, yes, look at our graph right here, as ln is going to negative infinity. So in other words, it's going downwards to negative infinity. In other words, the x value, or the an, is approaching 0. So as you're going to negative infinity, you're approaching 0. Yeah, so we have this going to 0, the an. Yeah, so this implies that inside goes to 0, even absolute value, doesn't matter. Yeah, because a number, as long as it's the same sign. Actually, no, I mean the same sign for the limit comparison test. But anyway, so this is going to, if the absolute value is going to 0, the an is also going to 0. So it could be going from the negative. Yeah, it's going to be alternating from the positive negative, but still going to 0. So let's again scroll up by the alternating series test over here. So yes, we have bn plus 1, or in our case, an plus 1 is less than or equal to an for all n, but in our case, n is greater than k, because all that matters is as it goes to infinity. And also the second condition, the limit goes to 0. So thus the series is convergent. So in other words, it converges for, so let's write this down. So thus by the alternating series test, the binomial series converges for where k is between -1 and 0. At the endpoint, x equals 1. And we'll summarize this all at the end. Also, here's just a quick note on pi product notation for factorials. So I've never covered this before, but this was included in the PDF lecture notes or the lecture PDF lecture proof that I was going over for the binomial series. And note that we can write the sequence an in pi product notation, and which is a more generalized notation for the factorial function. So that's our sequence. Let's look at absolute value of an. Actually, I'll get to that bit. So this is just a pretty interesting notation, especially when you're dealing with factorials that are beyond just integers. So the factorials from Wikipedia: factorial function is defined by the product n prime, or I mean n factorial. So n exclamation point. So 1 times 2 times 3 times 4 all the way until you get n minus 2, n minus 1 all the way till n. Like that. For integer, n is greater than or equal to 1. This may be written in pi product notation as n factorial. So you could write this as equaling to with this giant pi symbol from I equals 1 to n of I. Yeah, and you can write it like this, yeah, especially when you're not dealing with factorial, I mean, with integers. This is for integer, but this is more general. So that's our sequence, and let's look at absolute value of an, just because it was used in the PDF. So we're going to write this as absolute value of an. Remember, this equals to, the top is just going to be absolute value of k times k minus 1 times k minus 2, all the way until dot, 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 and then we get the last part is k minus n plus 1. And then we get, divide this by, and then divided by, it's going to be 1 times 2 times 3, put it under the correct one, and all the way up to n, like that. And then this is going to be 1 to the power of n, and this is at x equals to 1, so we'll put at x equals to 1. At x equals to 1, and now this part right here at the bottom is going to be our n factorial. So you could write this in a more general one. It was pretty interesting. It's pretty amazing shorthand as well. And here I'll just write it for n is greater than or equal to 1, just because otherwise you're going to have a 0 there. And you're dividing by 0 is undefined. That's why we would, by convention, just put n 0 factorial equals to 1. So anyways, just for this formulation, we're going to write this as for n is greater than or equal to 1, we get absolute value of an is equal to, and now we get, well, we could write this in pi product notation, because remember, these are all just products like this. This one considers by itself, yeah, this k over 1 times k minus 1 over 2. Yeah, so the general one is this one right here, so we could write this inside our pi product notation. I'm just going to write it like this, square box like that with that opening, just because it's a bit harder to write that. So anyways, it's going to go from I, so we can change a variable to I, up to n, and this is going to be, we're going to look at the absolute value of the general one, which is k minus, n is going to be replaced with I, plus 1 over I, like that. And then let's just simplify it further as we had done before. So we would divide out the i's and then leave this one, k plus 1 by itself. So this is going to be equal to pi product from I equals 1 up to n. And now it's going to be like this, k plus 1 over I minus 1. I over I is just 1, like that. And then as per usual, we know that, well, for k is less than 0 and greater than negative 1. Yeah, for this case, we know that, again, as per usual, if you just add 1 on every single term, so you're going to have 0 is less than is less than k plus 1, less than 1. And that's because, again, k, absolute value of k is less than 1, so then this k plus 1 is going to be less than 1. So thus, this is just to remove the absolute value sign, again, as we had done before. It's going to be k plus 1 over I, yeah, minus 1, like that. So that this absolute value sign, because this is k plus 1 is less than 1, you're dividing by this, it's always going to be just a fraction. Absolute value less than 1, and it's going to be positive, because k plus 1 is between 0 and 1. So then this is always going to be, just a absolute value less than 1. Then you're subtracting it by 1, you're always going to be a negative. So in other words, we can just flip it around, equals to 1 minus k plus 1. And remove the absolute value sign, like that. I just put this in just a little bubble, like that. So that we have that. Yeah, now that we have that, now let's just write down our an and without the absolute value sign in the pi product notation. So we have absolute value of an is equal to, just equal to pi product from I equals to 1 up to n. Right, it's a bit better. Let's see if I can write it better. Yeah, n I equals 1. and this is going to be from bracket 1 minus k plus 1 over I, like that. And bracket like that. And here I quickly just fix up this arrow and this box. So yes, that's what we have. Further now, so using comparison test, and we're going to look at the binomial series diverges when k is less than or equal to -1. So starting back from our earlier absolute value ratio at x equals 1, and when k is less than or equal to -1, we have, so I'll just write this down as recall. So recall our earlier ratio, an plus 1 over an is going to be equal to, and let's just scroll up and get a recap on this. Where was this? This goes all the way across in the ratio. So right here, so n minus k divided by n plus 1. This is at x equals to 1. So let's scroll up here, n minus k divided by n plus 1. So n minus k, and this is n minus k over n plus 1. And we get rid of the absolute value sign, and this is for n is greater than k. Because remember, all we're dealing with is, or wanting to deal with is as it approaches infinity. And then when it's greater than k, yes, we have n, yeah, like that. N is greater than k, so a larger number subtracted by smaller, you're going to get a positive number. So that's why we get rid of the absolute value sign. So now we're going to look at for k is less than 0. Again, we already have then we know that k is going to equal to negative absolute value of k. So it's just an easy way of seeing that. So absolute value of that, just put a negative because it's k is less than that. So just negative. If we have k is less than or equal to -1, then what we have is, well, absolute value of k. This one right here is always positive, so this is going to be greater than or equal to 1. So thus what we have is absolute value of an plus 1 over an is going to equal to n minus, and then minus, this is the k, minus, so n minus negative absolute value of k, like that. This is our n plus 1, which is equals to n plus absolute value of k, n plus 1, and where absolute value of k is greater than or equal to 1. So in other words, this is going to be greater than or equal to n plus 1 over n plus 1. So then these just cancel. We get equals to 1, like that. And then what we could do now is, well, we could just take this bottom part, the an, and move it over to the other side. Or move that away, take this part. Yeah, move it over to that side. So in other words, what we end up having is, move it over there. We're gonna get now, just put it like this: an plus 1 is greater than or equal to an. So yeah, this is we expect this to diverge. So in other words, the number is getting larger and larger. So let's just box this in like that. Yeah, so when we have this, in terms of what this means is, this just means that it's increasing. So the terms are increasing from, yes, an plus 1, absolute value is always going to be greater than the absolute value of an. Yeah, so the absolute values of the terms are getting larger and larger. So note that this doesn't meet condition I in the alternating series test, so we must use a different method. So if you scroll up over here, so yeah, we expect it to diverge. Because remember here, so this is for the alternating series test. So if bn plus 1 is less than or equal to bn, and we have the limit going to 0. So these are two conditions if the series is convergent. But does not state if the opposite is true. If it doesn't match any of these conditions, then it's divergent. It does not state that. So, but nonetheless, in this case, I've never seen any that wouldn't diverge in this case. So, MES important note, the alternating series test does not explicitly state a series is divergent if the test's criteria are not met for convergence. Nonetheless, I have not seen any scenario in which a series converges while the terms are increasing. That is when absolute value of an plus 1 is greater than or equal to an. Or actually, more specifically, this is when this is, put this insert button. Let's go insert greater than. Actually, we already have that in our calculator. Yeah, so in my keyboard. So the reason is because if it's equal to it, then that can happen when it's equal to 0, for example. So this increasing is always greater than. Yeah, because in case we have a scenario where it's equal to it, and then if it's equal to it and it's 0, so if they're all equal to and they're all equal to 0, then that's just a trivial case on most cases. So anyways, in our case, we can see that absolute value of an is greater than 1. Yeah, I just reworded this. So it's greater than or equal to 1, thus we can use the comparison test as follows, and I'll show you how it's greater than or equal to 1. So if we write our absolute value sign like this, and again, we're still at the endpoint x equals to 1. So this is going to be equal to absolute value k, then we have k minus 1, k minus 2, etc. all the way to dot, dot, dot. And we have k minus n plus 1. And then we also have, remember the x is 1, so this is 1 power of n. So that just goes away. So, like that. Now we have it. Divide this by n factorial, which is 1 times 2 times 3 times dot 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 all the way to n, like that. Yeah, so now this multiplication that we're doing right here, number k, so k is going to be equal to negative absolute value of k. So the larger the number, the absolute value sign, we want this to be as large as possible. So I'll just write it here for k is less than 0. Yeah, so let's put it like that. So 4k is less than or, just less than 0. It's going to be negative. Equals to k equals to negative absolute value of k. And thus, we have, if you look at this part right here, is all that matters, k minus n plus 1. And if we're looking at the absolute value of that, it's going to be absolute value. It's going to be greater than or equal to, greater than or equal to, and now we could just replace this with 1. Greater than or equal to when k is equal to negative absolute value of k. Actually, I better yet just put a negative 1 there. So this is for k is less than or equal to negative 1. So the absolute value of it, it's going to be, so this absolute value is going to be greater than whenever this is greater than this negative 1 there. So if a minus n plus 1, so then this cancels, this equals to negative n. Like that. And then, for example, if this was k equals to 2, then you're going to have negative n minus 2. So that's going to be a higher absolute value sign. Because all that matters is absolute value, we're looking at this absolute value. So thus, again, I'm doing all this work just because, for completeness, it does not state in the alternating series test that it is divergent if it's not met, but it's obviously going to be divergent. So anyways, this is going to be greater than when k is equal to negative 1. So we put a negative 1, negative 1 minus 2 is going to be, negative 1 minus 1 is going to be negative 2. This would be negative 3, because we have a negative 1 there. Dot, 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 all the way until, now we have this over here, k, this is going to be negative 1 minus n plus 1 is going to be negative n. Like that, and this one power of n just vanishes. It equals to 1. Divide this by, again we have our factorial 1 times 2 times 3 dot 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 times n. So in other words, this absolute value sign of this, get rid of all these negatives, becomes just 1 times 2 times 3 times 4, etc. In other words, this equals to n factorial. Get rid of the negatives over n factorial, and these just cancel. Equals to 1. So in other words, we have absolute value of an is greater than 1. So that's our comparison test. So we could just use it for the comparison test, and we know this one diverges. So thus we have absolute value from infinity, from n equals to 1 to infinity of an, like that. And this is going to be greater than or equal to the summation from infinity n equals 1. And this is because absolute value of an is greater than 1, greater than or equal to 1, as we just showed over here, as I had written it over there. Let's see if it's, yes, it's highlighted. Okay, let's highlight it again. Yeah, so this, do one more time. Okay, so that's the highlight. All right. So anyways, this, and let's just write this, not like a jaw, it's like someone biting something. So as soon as make it more straight. And this is infinity, n equals to 1, and this is going to be 1. And remember, this just equals to, well, 1 plus 1, etc., plus another 1. And it keeps going to infinity. So in other words, let's just go into infinity. This equals to infinity. So in other words, this diverges. So this goes to infinity, and this is greater than it, so thus this diverges. Because it's greater than another series that diverges. So that's the comparison test. So just put a check mark, because we were right as we suspected. Because it's pretty straightforward. And also because I've never seen one that would converge if it's increasing. If the terms are increasing, not necessarily the partial sum. So note that, so we keep going further. Note that we could have also used the test for divergence from my earlier video, since an does not approach 0 as n approaches infinity. In other words, an is greater than, we know it's greater than 1. So it's greater than 1, so in other words, it's not approaching 0, because it's always going to be greater than 1. So remember the earlier video, here's test for convergence. If limit as n approaches infinity of an does not exist, if the limit as n approaches infinity of an does not exist, or if the limit is not equal to 0, then the series an is divergent. So yes, so it is divergent, the series, because the terms aren't going to 0. So in this case, it's not going to 0. It's greater than or equal to 1. Let's keep going further. So trivial case is when k equals to 0, converges for all x. When k equals 0, the binomial series reduces to 1 by convention. And I'll show that in here in the summary. You could just see that when you plug in k equals to 0, everything just vanishes. All you're left with is initial 1. So anyway, so the binomial series, this is a summary to summarize everything. So the binomial series, and let's write this all out, is equal to, so this is 1 plus x, the binomial, and then to the power of k, where k is any real number, equals to, like that, infinity, n equals to 0, just for more general. Sometimes people use n equals 1. So k, from from k choose n, x to the n equals to summation infinity up to infinity from n equals 0, and then we have k over k minus 1, and then dot 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 all the way to k minus n plus 1 over n factorial times it by x to the power of n. So yes, fascinating stuff over here. And now this equals to 1 plus kx, and then plus k minus 1 over 2 factorial. So this is when n equals 0, just everything is just, by convention goes to 1, and we're just left with 1. And then plus k. So if k equals 0, these all just vanish. All the k's goes to 0. If it's 0. So everything vanishes after this. And yeah, let's just keep writing further. So this is going to be an x squared there. And then the next one's going to be, well, k minus 1, and then k minus 2, where, yeah, this is the same thing as k minus n plus 1. So this one, n is equal to 3. We're going to have negative 3 plus 1 is going to be negative 2. Divided by 3 factorial is going to be x to the 3. And then we're going to put a plus dot dot dot. It keeps going on and on. Let's put the dot more prominent, dot dot dot. Let's box this whole thing out. I just moved it over. Let's box this and see if I can get it in one try. And I think I can. Unbelievable. Alright, I just updated that actually, because the little part there was a bit not too perfect. Whoops. Alright, just fix that again. Let's just make this down. And just like that. And yeah, that's just perfect. Alright, so now that we have this, and the summation keeps going to infinity, so now this converges on the following intervals depending on the value of the real number k. So it's not just an integer for the binomial series. So if k is greater than or equal to 0, because remember when k is equal to 0, it converges for all x, so it doesn't matter. So yes, it converges, reduces to 1 by convention, just reduces to 1 there. So now this, the interval of convergence, and here I just wrote that a bit better. So converges on the following interval of convergence I, depending on the value of the real number k. So if k is greater than or equal to 0, and we know that I is going to be equal to, and again, let's just scroll up to what we had. Let's just keep scrolling up. So when when we have k is greater than or equal to 0, scroll up just to confirm. And just so we don't make any mistakes. So absolute convergence when k is greater than 0, this is for x is equal to 1. And also scroll all the way up here. Yeah, this is when, yeah, so k is greater than 0 converges for when x is at the endpoint -1. scrolling up here. So at x equals -1, it converges when k is greater than 0 and diverges when k is less than 0. And absolute convergence when x is equal to 1, which is the same as convergence. So let's just write this one down. So the interval of convergence is going to be square brackets, -1 and 1. And let's see if the screen comes back. Alright, the screen's back now, finally. Alright, and now this is going to be -1 is less than or equal to, just write it like this so we know what the square brackets mean, and less than or equal to 1. Yeah, so x is greater than or equal to -1 and less than or equal to 1, like that. And now the next scenario is if k is less than 0, yeah, less than or equal to 0, and greater than -1. And also here's less than or equal to 0, because again it always converges when k is equal to 0 by convention. So now I is going to equal to. So now let's scroll up here, and yes, this one is scroll up all the way across to here. Yeah, scroll up to this one here. So when x is equal to 1, the binomial series converges for -1 from k is between -1 and 0. So it converges by the alternating series test. But then remember earlier for the x equals to -1 is divergent. So when k is less than 0 for at the endpoint x equals -1, the binomial series diverges. So in other words, -1 is not the endpoint, it diverges on that, but converges on the x equals 1 endpoint. So let's just write this all down. Again, just scrolling, just make sure everything's in order. So this is going to be open bracket. Yes, put it like that. So open bracket -1, so it does not converge there. And then it converges at the +1 endpoint, so close bracket. And this is going to be -1. You could write this the same thing as writing -1 as x is greater than -1, but less than or equal to -1, like that. Oh, I mean +1. So x is less than or equal to +1, but greater than -1. And that's why we have this open bracket, for it does not equal there, and this closed bracket means it equals at the endpoints. And remember the open and closed intervals as explained in one of my earliest videos. So now it's if that. Now the next one. So if k is less than or equal to -1, then what we have is, I. This is scrolling up here again. This diverges for all of them. So note that we also use the test for divergence. So this a does not approach 0 as n approaches infinity. Well, that's actually using test for divergence there. Yeah, so for n is for k is less than or equal to -1, it diverges as a series. We use the we use a test for test for divergence, and we also use the comparison test over here, and just scroll up over here. So this is diverges when k is less than or equal to -1. This is at the endpoint x equals to 1. And the other endpoint, we already showed that it's for k is less than 0. So this will have open brackets on both of them. -1 and +1 is the interval. And remember, the ratio test showed that absolute value of x is less than 1 is the interval of convergence, or the radius of convergence. And now at the endpoints, we have to do this specifically. So now the interval is going to be like this: -1 less than 1. So yes, this is fascinating stuff. So all that work just to show this little box. And yeah, now we're finally done. So this deserves a hashtag amazing stuff. And also, MES note, this video took a lot of energy out of me in the making of it. Haha. And this is a tongue-in-cheek. So yes, it's pretty pretty epic. Most of the energy came from trying to figure out what the binomial series PDF proof was like. That lecture notes was absolutely mind-boggling. Why didn't they just explain certain things? They don't need to go as this in depth as I do, but this is for my own sake and for whoever's watching, so that this will stand a test of time, in my opinion, as the most comprehensive derivation and proof of the binomial series and the Raabe's test and the Kummer's test. Anyways, that's all for today. Let's just scroll up, and yeah, the computer screen keeps glitching, but I found a way to make it not glitch as much, and I'll do a video on that later. And it's just basically turning off all permissions for using the background processes and folders and etc. for this one. Anyways, keep scrolling up. That is all for today. Like always, you can view these exact notes in the link in the description below, as well as you can see them in PDF format or in article format on the Hive blockchain. And yeah, it's pretty amazing there. And just keep scrolling up. Anyways, that is all for today. Thanks for watching, and stay tuned for another Math Easy solution.